Every year, the world produces over 500 million tons of glass. Without it, there'd be no windows, smartphones, cars, or skyscrapers. But few people know that the journey to this perfect transparency doesn't start with glass at all. It starts with hot sand, heated in furnaces to temperatures exceeding 1600 degrees Celsius. This isn't just manufacturing, it's modern-day alchemy. Millions of tons of sand transformed into an ocean of molten glass, floating on liquid tin to create a perfectly smooth surface. You're about to discover the secrets of this process right here. Before hot sand becomes a transparent window, it all begins in a quarry. The primary raw material for float glass is high-quality silica sand. It must be almost perfectly pure, with a silicon dioxide content exceeding 99.5%. This sand is extracted from special deposits, typically deep underground. One of the most prized is Ottawa sand from Illinois. Pale white, fine as flour, and exceptionally pure. Quarries operate like giant anthills. Excavators tear through layers of earth, whilst lorries, 40-tonners, haul the sand to crushing plants. Then comes dry screening. The sand is cleaned of stones and the slightest impurities. Besides sand, glass contains several other components. Soda ash lowers the melting temperature. It's transported from salt deposits, particularly from Wyoming, in 23-kilogram bags or in bulk. Limestone stabilizes the structure. It's supplied from quarries and ground to a dust with particles under 1 millimeter in diameter. The mix also includes dolomite, aluminum oxide, saltpeter, and glass waste, what's called cullet. Cullet reduces the energy consumption for melting by up to 25%. After initial cleaning, all components are mixed in precise proportions, which are kept as trade secrets. A giant mixer the size of a 2-story house prepares the glass flour mixture. The finished mixture is transported to production by lorry and sometimes by rail or even on barges. Storage temperature must be controlled, no moisture whatsoever. The warehouse resembles a sterile grain elevator with silos, each with a capacity of roughly 560 cubic meters. The mixture is then automatically fed into the glass furnace, where within just minutes, everything that was sand and dust yesterday transforms into a boiling ocean of glass. The mixture enters the heart of production, the glass furnace. It's a genuine industrial volcano, over 60 meters long, with temperatures reaching 1600 degrees Celsius at the melting core. Raw materials are fed in automatically, several tons per hour. In the first 9 to 12 meters of the furnace, melting occurs. Components melt and merge into a glowing, viscous mass. Next comes the homogenization zone. The mass is stirred and matures until all bubbles and lumps disappear. And only then does it gently flow onto metal. This is where the magic begins. In the second stage, the mass enters a bath of molten tin heated to 1100 degrees. The glass literally floats on the metal, spreading into an even ribbon. Thanks to surface tension and the perfect flatness of the tin, a mirror-smooth surface forms on both sides, without polishing, without presses. Thickness is controlled by stretching, special rollers, or electromagnetic fields either stretch or compress the glass ribbon. This way, the output can be glass ranging from 1.5 to 19 millimeters thick. The tin bath spans over 45 meters, and the glass slowly floats along it at speeds up to 7.5 meters per minute, cooling en route to 540 degrees Celsius. This is an absolutely critical moment, but even at this stage, it's not ready yet. Next comes the annealing zone. The glass ribbon passes through a long tunnel where it cools by several degrees per minute to relieve all internal stresses. Without this, the glass could later crack on its own. Its surface is like ice, smooth without a single scratch. The sheet size is impressive, up to 3 meters wide and over 9 meters long. In this state, the glass enters the cutting zone. Before it's cut, a computer scanning system analyzes the entire surface, searching for micro cracks, inclusions, stress points. Any find means that sheet's rejected. Cutting isn't mechanical anymore. Now it's laser or roller scoring. A microblade, similar to diamond, scores a line, and then gentle pressure snaps the glass precisely along that path. Sometimes sheets are cut straight to order, say 60 by 90 centimeters for construction glass or screen size for Tesla. Others go in standard formats to warehouses, where they're stored vertically on racks with rubber spacers. After cutting comes the calibration stage. Sheets are checked for thickness, geometry, straight edges. High-definition cameras scan every centimeter. Lasers analyze the corners. There are almost no human hands here, only at the final stage when workers in gloves mark the perfect sheets. In a world where glass has perfect transparency, marking is its name, passport, and craftsman's signature all in one. It's in the marking zone that each piece of glass is given its identity: where, when, by whom, and for what purpose it was created. The most common method is laser engraving. A special laser burns microscopic dots onto the surface, creating an indelible frosted inscription. Font thickness is less than 2.5 millimeters. This inscription can't be removed without damaging the glass, which is precisely why it's often used as an anti-tamper code. Sandblasting is used for decorative or premium glass. Through a stencil, abrasive is applied to the glass under pressure, forming a raised frosted mark. Then there's marking with ceramic inks. This method is used at the stage before tempering. Special paint is applied by printing, then baked at temperatures exceeding 1100 degrees. This marking is colored, noticeable, and extremely durable. It won't wash off, won't wear away, and won't fade. Marking can be either technical or branded. For instance, windows in luxury homes often proudly display the manufacturer's logo. In some projects, marking is even used for authenticity verification. For example, glass for armored vehicles or government buildings receives a serial number in QR code. The final stage is documentation. Every sheet gets a record in the system, like in a hospital. What sort of patient it is, when it was born, what properties it has, and where it's heading. This matters because glass isn't always dispatched immediately. Some batches are stored for months until their time comes. Every year, humanity discards more than 10 million tons of electronic waste. Of this, hundreds of thousands of tons are televisions, packed with precious metals, complex plastics, and even deadly toxic substances. But what happens to them after they leave our homes? Did you know that inside one old, bulky television set lies pure gold, silver, and components that could become the heart of new gadgets? This isn't just recycling. This is a high-tech treasure hunt. Today, we'll show you how the most advanced recycling facilities operate and why this process matters more than you might think. It all starts not at the factory, but in our homes and offices. Old, outdated devices are collected at specialized reception stations. In developed countries, this is a well-oiled system, from dedicated containers in supermarkets to trade-in programs run by major retailers. Modern recycling centers aren't grim rubbish tips, but gleaming high-tech facilities. Their primary goal is to extract all reusable materials as efficiently as possible, while safely neutralizing the toxic components hidden inside. At large-scale operations, television recycling is organized along automated production lines, where most processes are carried out by machines rather than people. The first stage at the facility is the medical examination and sorting. Televisions are separated into three main categories: bulky cathode ray tube monsters from the past, slimmer plasma panels, and modern liquid crystal displays. Each type requires its own entirely unique approach. Then the undressing begins. Robotic manipulators or workers strip away the plastic casings. This plastic is immediately sent to giant shredders where it's ground into tiny fragments which, after remelting, will become parts for new motor cars or casings for other electronics. Metal frames and fixings are also separated and sent to their own recycling line. Once the casing is removed, the defenseless innards of the television move on to the dismantling line. Old cathode ray tube televisions receive particular attention. They can genuinely be described as environmental dirty bombs. The most hazardous component is the cathode ray tube itself. It contains up to several kilograms of lead, which was used to prevent X-ray radiation, whilst the internal surface is coated with a layer of phosphor containing toxic rare earth metals. Consequently, they're dismantled with exceptional care, often by hand, within sealed chambers. First, a specialized heated wire or laser carefully separates the front clean glass from the rear lead-laden funnel. The glass is then cleaned, crushed, and sent for recycling, whilst the lead is extracted for manufacturing new batteries. Modern liquid crystal displays are no less hazardous. Hidden along the edges of the panel, thin as spaghetti, are fluorescent backlight tubes. Each of these tubes contains a small but highly dangerous amount of mercury. That's why LCD panels are dismantled in specially sealed boxes with powerful ventilation systems. Robotic arms or workers in protective suits carefully extract these tubes. They're placed in hermetically sealed containers and sent to specialized facilities where the mercury is safely extracted and purified for reuse. The liquid crystals sandwiched between the glass layers present another challenging component. They're extracted using chemical solvents. Plasma panels require their own approach. Unlike LCD displays, they don't contain mercury, but their cells use inert gases such as xenon and neon. The panels are dismantled, the gases are collected in special containers for reuse, whilst the high-quality glass that makes up the screen is crushed and purified. Once the screens and casings have been neutralized and sent on their separate ways, the most valuable parts remain on the conveyor belt, the circuit boards. This is where the precious metals are hidden. Copper wires, aluminium heat sinks, and other metallic components are separated and sent off for smelting. The most important and complex part is processing the printed circuit boards. It's in these boards, within the microchips and connectors, that you'll find microscopic yet incredibly valuable quantities of gold, silver, palladium, and other precious metals. First, the boards are shredded into fine particles. These particles are then sent to the chemical workshops. The most common extraction method is chemical leaching. The shredded boards are immersed in special acid solutions. To extract gold, they often use aqua regia, a mixture of concentrated hydrochloric and nitric acids, which can dissolve even this noble metal. After the precious metals have dissolved into the solution, the precipitation process begins. Special chemical substances are added to the liquid, which cause the pure metals to fall out as sediment. For instance, ferrous sulfate is used to precipitate gold. This gold sediment is then thoroughly washed, dried, and remelted into small but incredibly valuable ingots. Similar methods are employed to extract copper and silver, though using different, less aggressive acids or the electrolysis method. In the final stage, all the recovered materials, gold, copper, aluminum, glass, and plastic, are compressed into compact blocks. Each year, millions upon millions of televisions are discarded worldwide, with their combined weight running into millions of tons. In Europe alone, for instance, electronic waste exceeds 10 million tons annually, and a substantial portion of that comprises televisions and monitors. This staggering figure isn't merely a statistic, it's testament to our rapid technological advancement and its darker consequences. But there is encouraging news. Year on year, growing numbers of people are recognizing the importance of proper disposal. Hundreds of thousands of tons of old televisions now find their way to recycling facilities each year, helping us preserve our air, water, and finite natural resources. Here's what the real secret we mentioned at the beginning is all about. Your old television isn't rubbish, it's a genuine urban mine. A single ton of old circuit boards contains 40 to 50 times more gold than a ton of gold ore extracted from a traditional mine. Electronics recycling isn't simply about caring for the environment, it's an incredibly profitable business of the future. We've learned to extract the most valuable resources not from beneath the ground, but from what we ourselves have created and discarded. And every time you take an old television for recycling, you're not just getting rid of clutter. You're returning precious metals to the economy and helping to make our world a bit cleaner.
Picture a metal that's everywhere in nature, yet remains one of the most expensive and difficult materials for industry to work with. That metal is titanium. It's abundant in the Earth's crust, but producing it is so labor-intensive, energy-hungry, and technologically finicky that the aviation industry literally fights for every quality pound. And that's not an exaggeration. Without titanium, there'd be no modern jet engines, no critical aircraft components, no landing gear parts, no structural elements where you need high strength, low weight, and corrosion resistance all at once. But the journey of titanium from black sand or ore concentrate to an aircraft part is remarkably far from conventional metallurgy. You can't just melt it down, reduce it with carbon, and pour it into a mold like steel or iron. Titanium is too reactive. It bonds with oxygen way too easily. It's too sensitive to contamination. And that's exactly why producing titanium for aviation isn't just mining and smelting. It's one of the most complex sequences of chemical and metallurgical operations in modern industry. In nature, titanium almost never occurs as pure metal. Industry extracts it from minerals, mainly rutile and ilmenite. Very often, these ores aren't mined in classic deep mines, but in what are called mineral sands, placer deposits that form along coastlines and in ancient sedimentary zones. This means the first stage of titanium production looks totally different from the typical picture of miners and mine shafts. Here, they might use dredges, excavators, washing systems, gravity and spiral separators that separate heavy minerals from lighter waste rock. But even after processing, what you have isn't metal yet. It's just titanium-bearing raw material. And this is where the main paradox kicks in. Titanium is extremely abundant, but extracting actual metallic titanium from its oxides is way harder than smelting many far rarer metals. That's exactly why titanium is expensive, not because it's rare in nature, but because turning ore into aviation-grade metal is brutally complex. The next stage is converting the ore into a chemical form from which pure metal can actually be extracted. For titanium, this is especially critical because the usual heat-based reduction doesn't work here. While iron or copper can be processed using relatively straightforward metallurgical methods, titanium is a different beast. Its oxide is too stable, and the metal itself, at high temperatures, binds too aggressively with oxygen, nitrogen, and carbon. So industry takes an indirect route. Titanium feedstock is first converted into titanium tetrachloride, a volatile chemical compound that can then be purified. To do this, the concentrate undergoes high-temperature chlorination in the presence of a reducing agent, and then the resulting product is sent for purification. The key advantage of this approach is that titanium tetrachloride can be purified through distillation, removing a whole range of unwanted impurities. Essentially, this is the moment when rough mineralogy transforms into chemically controlled feedstock for the metal to come. And it's at this stage that it becomes clear. Titanium production isn't classic smelting. It's a chemical metallurgical process with extremely tight purity requirement. Once the purified titanium tetrachloride is ready, one of the industry's most critical processes kicks in, the Kroll process. This is the fundamental industrial technology that makes modern mass production of titanium for aviation, aerospace, and other high-tech fields even possible. Here's how it works. Purified titanium tetrachloride reacts with molten magnesium inside a sealed reactor. The result? The metal breaks free from chlorine and forms what's called titanium sponge. This isn't a solid ingot or finished semi-product yet. It's a porous, brittle metallic mass that looks like hardened porous rock. After the reaction, leftover magnesium and byproducts get removed. Then the sponge is sorted, crushed, and prepped for the next stage. At first glance, you might think the sponge is almost finished metal, but really, it's only halfway through a long journey. Aviation doesn't just need titanium. It needs material with precise chemical composition, high uniformity, and predictable behavior under stress. So next, this sponge still has to be transformed into a full-fledged structural metal. The next major stage is remelting the titanium sponge into a dense, homogeneous ingot. And this is where production gets especially tricky again. Molten titanium aggressively absorbs oxygen, nitrogen, and other impurities from the surrounding environment. Even slight contamination can make the metal brittle and unsuitable for critical aircraft components. That's exactly why titanium remelting doesn't happen in a regular shop floor atmosphere. It's done in a vacuum or a controlled inert environment. One of the key methods is vacuum arc remelting. For this process, they form a consumable electrode from titanium sponge, alloying additives, and sometimes a portion of quality scrap returns. Then, this electrode is gradually melted by an electric arc, and the metal collects drop by drop in a water-cooled mold, forming an ingot. For critically important aerospace applications, a single remelt like this often isn't enough, so the metal may go through double or even triple remelting to achieve maximum structural uniformity, stable composition, and the absolute minimum number of defects. But aviation doesn't just need pure titanium. In most cases, the foundation is special titanium alloys, and the most famous of these is Ti6Al4V, also known as Grade 5. In this material, titanium is alloyed with aluminum and vanadium to achieve a combination of properties that's practically impossible to replicate in many other metals. This alloy is noticeably lighter than steel, yet it has very high specific strength, good fatigue resistance, and outstanding corrosion resistance. That's exactly why it's used in compressor discs and blades of aircraft engines, in landing gear components, structural load-bearing elements of the aircraft, and other assemblies where every pound matters. But for titanium to become a true aerospace material, it's not enough to just melt it into an ingot. What follows is forging, rolling, heat treatment, microstructure control, and mechanical property verification. In other words, aerospace-grade titanium isn't just a metal, it's an entire series of carefully sequenced operations, each one affecting the final reliability of a part that will later operate under enormous loads. This is where it becomes clear why titanium is so expensive. First, production isn't continuous, it's largely cyclical. The Kroll process is slow and energy-intensive. It requires magnesium, chlorine, sealed reactors, and complex purification afterward. Second, almost every hot stage demands a vacuum or inert atmosphere. Why? Because the metal reacts too aggressively with oxygen. Third, titanium itself is a nightmare to machine. It has low thermal conductivity. Heat doesn't escape into the chips. Instead, it concentrates on the cutting tool. This accelerates tool wear, slows down machining speeds, and drives up the cost of every finished part. On top of that, titanium semi-finished products require extremely precise control of structure and chemistry, and tolerances in aviation are far tighter than in mass industry. The bottom line? Titanium isn't expensive because it's rare in nature. It's expensive because the entire chain, from ore to aerospace-grade alloy, is extraordinarily complex, long, and sensitive to any deviation from the process. There's one more reason titanium is so valued specifically in aviation. It fits perfectly into the philosophy of modern engineering, where weight savings directly translate into efficiency gains. A lighter aircraft burns less fuel, carries more payload, and its engine and structural components operate in more favorable conditions. But titanium isn't a universal replacement for steel or aluminum. It's used where it truly justifies its cost, in hot sections, highly stressed components, corrosive environments, and parts where the combination of strength and low weight is critical. That's why titanium production for aviation isn't just metallurgy for the sake of metal. It's an industry where every step serves a single purpose: to create a material that will perform reliably in an aircraft at high speeds, under cyclic loads, vibrations, temperature swings, and with enormous responsibility for safety. When you look at titanium's entire journey, you're witnessing a nearly perfect example of modern high-tech manufacturing. First, heavy mineral sands or ore concentrates get separated from waste rock. Then, chemical processes transform the raw material into purified, volatile compounds. Next, through the Kroll process, they obtain porous titanium sponge. After that, it's remelted into ingots under vacuum, alloyed, structurally and chemically refined several times over, and only then transformed into semi-finished products and parts for aviation. In other words, titanium's journey is a path from dirty natural mineral to a material that can work inside a jet engine or an aircraft structural assembly. And perhaps that's where titanium's real power lies. It seems like just another element in Earth's crust, but actually becomes a true engineering marvel only after incredibly complex technological processing. That's why aviation-grade titanium isn't just a metal. It's the embodiment of how far industry can push when it needs the perfect balance of strength, lightness, durability, and reliability.
Every year, the world produces over 500 billion glass bottles. If you line them up in a single row, they'd wrap around the Earth more than 3,000 times. These are mountains of gleaming, fragile material that could remain in landfills forever, forming glass deserts for thousands of years. But a portion of this material gets a second, third, 100th chance at life. How exactly does an ordinary lemonade bottle, tossed into a recycling bin, pass through fire and mechanical hell to become crystal clear and ready for use again? Behind this lies a colossal technological process that rivals space programs in precision and scale. If you watch to the end, you'll discover the main secret of why glass is called the immortal material, capable of infinite reincarnation without losing quality. And it's precisely this property that makes it a genuine marvel of engineering and ecology. The journey to glass rebirth doesn't start at a factory. It starts on our city streets. Recycling begins with collection. In advanced countries like Germany or Switzerland, this is a well-oiled system where every citizen plays a part. Special containers for clear, green, and brown glass stand on every corner. Moreover, in many European countries, there's a fond system, a deposit included in the beverage price. By returning an empty bottle to a special machine at the supermarket, you receive a voucher that can be used towards purchases. This transforms rubbish collection from a duty into a profitable venture. In other regions, there's an entire shadow army of collectors, people for whom returned bottles are their main source of income. The collected glass flows along logistical arteries, from small trolleys to massive refuse lorries towards recycling plants. It's here, on these noisy and dusty sites, that the first act of its resurrection begins. After tons of glass bottles arrive at the plant, they face their first test, sorting. And this is where technology worthy of science fiction enters the game. Along a wide conveyor belt rushes a motley stream. Clear bottles from water, green ones from wine, brown ones from beer. The human eye can't keep pace with this speed. So optical scanners based on near-infrared technology are installed above the conveyor. A light beam penetrates through the glass while sensors analyze how it refracts. Artificial intelligence determines the chemical composition and color of each fragment in fractions of a second. Color sorting is critically important. Just one green bottle can contaminate an entire ton of raw material for clear glass, giving it an unwanted tint. After identification, the system issues a command: Powerful jets of compressed air shoot with surgical precision at the right fragments, knocking them off the conveyor into separate compartments. But color is only half the battle. Along with glass, the stream contains numerous foreign objects: metal caps, plastic rings, paper labels. Here begins multi-level cleaning. First, the conveyor passes under giant electromagnets. With a deafening clang, they snatch all steel caps from the stream. Then, eddy current separators come into play. They create a magnetic field that repels non-ferrous metals, like aluminum, forcing them to literally jump off the belt into a separate container. After this, powerful fans blow away light rubbish, paper and plastic. And finally, the glass passes through a water cleaning system where organic residue and dirt are washed away. Just imagine the complex journey every bottle we discard takes before becoming clean raw material. After sorting and cleaning, the glass is sent to its execution, the crusher. This is an enormous machine whose steel jaws or hammers grind entire bottles into small fragments with a deafening roar. The sound is as if thousands of chandeliers are simultaneously shattering. Several types of crushers exist: jaw crushers that crush glass between two plates, and hammer crushers where hammers spinning at furious speeds smash glass against a steel wall. This stage's goal is to transform bulky and fragile bottles into a uniform mass called cullet. This material is far more convenient for transport and, most importantly, for melting. At this stage, any remaining impurities not removed earlier can be additionally screened out. After crushing, the cullet is sieved through a system of vibrating screens that calibrate it by size. Even after crushing, cullet may contain microscopic metal or organic particles invisible to the eye, so it undergoes final, even more thorough cleaning. Magnetic separation here works at a new level, capturing the tiniest metal inclusions. Then special optical technologies are used to remove ceramic or porcelain remnants, which look like glass but have different melting temperatures and can cause defects in the finished product. This guarantees that absolutely clean material enters the furnace. Then the glass crumb is sent to vibrating sieves, where it passes through several levels of screens with different mesh sizes for separation into fractions. Different grain sizes are used for different types of products. This entire process is fully automated, minimizing risks for workers. After all stages of cleaning and calibration, the purest cullet is sent to the factory's heart, the melting furnace. At the plant, it's loaded into gigantic furnaces where it melts at temperatures from 1530 to 1650 degrees Celsius. At such heat, glass becomes liquid, viscous, and fiery red, like lava. Adding cullet to the melting process is not just ecological genius, but economic genius too. Recycled glass melts at a lower temperature than primary raw materials, sand, soda ash, limestone, which reduces energy consumption by 30%. Sometimes a small amount of new raw material is added to the melt to adjust the chemical composition and guarantee the strength and transparency of future products. After the glass transforms into a uniform liquid mass, its rebirth begins. The molten lava is directed into forming machines. Here, a drop of molten glass under air pressure transforms into a new bottle, jar, or vase in seconds. At large plants, this process is fully automated and can include high-precision molds to ensure perfect quality. Immediately after forming, the red-hot glass products pass through a long annealing tunnel, where their temperature gradually and very slowly decreases. This is a critically important stage that relieves internal stresses in the glass and prevents cracking. After forming and cooling, new glass products undergo ruthless quality control. Special robotic systems check every bottle for the slightest defects, air bubbles, micro cracks, uneven wall thickness, or incorrect shape. Optical scanners and lasers illuminate the glass, revealing flaws invisible to the eye. If a product doesn't meet the highest standards, it's ruthlessly rejected and sent back for remelting. Then, bottles are tested for mechanical strength, checking whether they can withstand the pressure of carbonated drinks and impacts during transport. Only after passing all these tests are new glass products packaged and dispatched to market. Thus completes one cycle of their endless life. Imagine a single thread capable of holding the weight of a skyscraper, strong enough to ride out a storm over the ocean or to lift a drilling rig from the depths of the sea. How is this living armor born from a cold piece of steel in a world where weakness is not an option? Why does the fate of a billion-pound project hang on a microscopic flaw in a single wire? We will journey from the searing heat of the furnace and giant carousel machines to the most brutal tests of strength and endurance, where the line is drawn between what will hold and what will break. Watch to the end, and you'll uncover a secret that will make you look at a simple steel cable in an entirely new light. You'll find them at work in maritime cranes, hoisting modules onto oil platforms, deep in mine shafts, erecting wind turbines in the middle of the ocean, and in the construction of monumental bridges and skyscrapers. The material used to create these immense ropes is a high-alloy carbon steel, but not just any steel. This is a grade perfected with alloys. Chromium, nickel, and sometimes molybdenum are added to the mix, each with a specific purpose. Chromium enhances corrosion resistance, while nickel adds strength and ductility. These elements transform the metal into a form of engineered armor. And to prepare this steel for weaving, it must first be drawn into wire. The initial stage is rolling. Steel billets are passed through rollers, progressively reducing their diameter. Next comes thermal quenching. The wire is heated to extreme temperatures and then rapidly cooled to create a precise molecular structure, making the steel both hard and resilient. The third step is coating. This is chosen based on the final application: a zinc coating, galvanizing for protection against rust, or a polymer sheath for operating in aggressive environments like saltwater. But even after all this, it is not yet a finished wire. Now comes computerized calibration. Each wire is inspected by high-precision machines, measuring not only its diameter down to the micron, but also checking for microbends, tension, and symmetry. A deviation of 1/100th of a millimeter could be critical, because thousands of these wires will soon act as one. A single weak segment creates a potential point of failure. Once every wire has been treated, tested, and calibrated, one of the most spectacular stages begins: the stranding of the rope. And this isn't simply twisting wires together. It is a mathematically precise system of tension, angle, and the interplay of hundreds of individual elements. At the heart of every rope is a core, which can be steel or a synthetic fiber. It is around this core that strands of steel wire are laid in spirals. Each strand can contain dozens, even hundreds of wires, all woven in a strict, predetermined pattern. The goal is to distribute the load perfectly evenly along the entire length. Every rope has its own configuration, the angle of the lay, the number of strands. For flexibility, more thinner wires are used. For rigidity, fewer but thicker ones. The process takes place on giant stranding machines that operate like carousels. They rotate slowly, methodically, drawing individual wires from dozens of bobbins. A single machine can construct a rope over 100 meters long. As it's woven, every single wire is held at a precise tension, managed in real time by an automated system. If just one wire is twisted or over-tightened, the rope could lose its integrity. The entire operation is continuously monitored. Sensors detect the slightest vibration, and the machine will halt automatically if a fault is found. Human oversight here is minimal. Interestingly, some ropes have a composite structure, an outer layer with polymer insulation or fire-resistant coating housing internal metallic strands with different properties. When the stranding is complete, the rope is still not ready. It now faces one of its most critical trials, testing and certification. This is where it must prove it can handle the forces it was designed for. The first test is for breaking strength. The rope is secured between two colossal hydraulic grips, which then begin to pull with incredible force. We are talking about hundreds of tons of load, gradually increasing. The aim is to find the ultimate tensile strength. Ideally, the rope must withstand 3 to 5 times the load it will carry in the real world. But surviving maximum force isn't enough. It also undergoes a fatigue test, where the rope is repeatedly tensioned and relaxed, simulating thousands of real-world operational cycles. Separate tests are conducted for torsion, where the rope is twisted to assess its rotational stability. This is vital for applications where the load vector is constantly changing. Another critical phase is the environmental trials. The rope is submerged in salt water, frozen to -40 degrees Celsius or heated to over 100 degrees. Some are tested for resistance to UV radiation, chemicals, or even fire, because the conditions on a North Sea oil rig or in a mine shaft are nothing short of extreme. Only after passing this battery of tests can a rope receive certification from international bodies like Lloyd's Register or DNV. Every rope is given an individual serial number linked to its testing protocols. In some cases, its pedigree is even recorded, showing which steel mill produced the metal for every single wire. Once it has passed every trial, the rope is wound onto enormous reels, 20, 50, or even 100 meters long, and transported on special platforms. A single reel can weigh several tons. On site, the rope is installed with millimeter precision, and only after a final inspection does it begin its work in a world where there is no margin for error. Every year, aircraft around the world cover more than 25 billion miles. That's roughly 26,000 trips around the Earth. And it's all thanks to the heart of aviation, the turbofan engine. Inside, there's a genuine inferno where temperatures reach over 1,100 degrees Celsius. But how can a machine made of metal survive where steel melts? How do they craft blades with micron-level precision that spin faster than a bullet? And why are some components today literally grown from powder using lasers? Stay with me till the end, and you'll discover a secret that'll forever change how you think about engineering. Turbofan engines that power the giants of the sky, Boeing and Airbus aircraft, seem like something out of science fiction. Yet they're the genuine embodiment of engineering brilliance. How do you assemble these remarkable machines from tens of thousands of parts and materials like pieces of a puzzle? Ordinary metals simply won't do for their manufacture. The engine must operate in conditions where temperatures can exceed 1,100 degrees Celsius. It's a proper inferno, and ordinary steel simply wouldn't cope. This is where titanium alloys enter the picture. Lightweight, robust, and capable of resisting melting in extreme heat. And for the hottest zones of the engine, they use nickel-based superalloys. Such extreme temperatures arise from the fuel combustion process in the combustion chamber. During engine operation, aviation fuel, typically kerosene, mixes with air and ignites, creating hot gases. These gases literally accelerate to extraordinary speeds and temperatures, over 1,100 degrees Celsius, sometimes reaching 1,500 in modern engines. This level of heat is essential to achieve maximum efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that drives the turbine and propels the aircraft. Here lies the principal challenge. The engine must not only withstand these extreme conditions, but also operate reliably. You know what's remarkable about the engine manufacturing process? Even individual components, such as turbine blades, are crafted with micron-level precision. For instance, blades are cast in a vacuum to ensure there isn't even the slightest crack inside. Some are formed to have a single crystal structure, meaning the metal has not a single seam. But that's not all. Three-dimensional printing? Yes, that's used too. For instance, for complex components that are impossible to create through traditional casting. Turbine blades are the engine's heart. They operate in the hottest zone and convert the energy from hot gases into rotational movement. First, a blade model is created from wax. Then the show begins. In a special furnace, superalloys are melted, composed of nickel, chromium, and other metals capable of withstanding temperatures above 1,100 degrees. This molten metal is poured into a ceramic mold. But the secret lies not only in the material, but also in how it's done. To ensure the blade withstands tremendous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams or microcracks. Why does this matter? Seams or microcracks in such conditions are like a minefield. One error and the blade fails. Single crystals are grown through very gradual cooling. Once the metal cools, the ceramic mold is broken away and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface. And so, each blade is inspected individually. If there's even the slightest defect, it doesn't proceed further. Fuel injectors, combustion chamber components, or even compressor blades in aviation are manufactured using three-dimensional printing. For instance, GE Aviation prints injectors for their engines that weigh 25% less but are 5 times stronger than traditional ones. Layer by layer, from powder and light, components are created that allow aircraft to fly faster, further, and more efficiently. First, engineers create a digital three-dimensional model of the component with maximum precision. Here, every curved surface or cavity matters. Why? Because these components often operate in places where a millimeter can change everything, from engine efficiency to its reliability. Instead of the usual chunk of metal, they use ultrafine powder here, for instance from titanium, nickel, or Inconel. It resembles sand, but with particles so minute they're barely visible to the naked eye. The powder is poured into a special reservoir, and it becomes the building material. The printer's working principle is straightforward yet brilliant. It melts the powder using a laser or electron beam. The laser heats the powder to such a temperature that it literally fuses into a uniform metallic structure. Then the next layer of powder is applied and the process repeats. This method is called selective laser sintering or melting. And here's what's splendid. Three-dimensional printing allows the creation of even the most complex geometrical forms. For instance, components with internal cooling channels that simply cannot be manufactured through casting or milling. You see, in traditional manufacturing, you often need to create a large component first, then cut away everything superfluous. The resulting component isn't quite ready yet. After printing, it undergoes heat treatment, heated and gradually cooled to relieve internal stresses in the metal. Then comes final grinding, polishing, or mechanical processing if precision needs correcting. And naturally, each component passes rigorous testing. After all, this is serious business. If a component can't bear the load, the consequences could be catastrophic. Engine assembly takes place in an enormous hangar, where every square foot is occupied by tools, engine parts, and people in overalls. Everything begins with the engine casing, resembling a gigantic metal cylinder. This is the skeleton to which all other parts will be attached. The casing is crafted from titanium or nickel alloys, as it must withstand tremendous loads. Engineers work like watchmakers. The casing is secured in an enormous machine to ensure everything is absolutely straight. Next come the compressors, several rows of blades responsible for compressing air before feeding it into the combustion chamber. Blades are installed one after another. Each is inspected manually. Following the compressors comes the turbine stern. Next, the combustion chamber is installed, the engine's genuine inferno. Here, compressed air mixes with fuel and burns. Engineers install special injectors that ensure uniform fuel delivery. And here, everything must be perfect. An incorrect injector angle, and the engine could lose efficiency or even fail. Running through the entire engine is a central shaft, a sort of backbone. At one end of the shaft, the fan is mounted in the form of an enormous wheel at the engine's front, whilst at the other end sits the turbine. To install the shaft, they employ special robots. Once the engine's internal section is assembled, external systems are added. Fuel pipes delivering combustion to the combustion chamber. The oil system, ensuring lubrication of all moving parts. And electronics, because the engine is literally packed with sensors monitoring temperature, pressure, revolutions, and much more. These elements are secured using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After assembly is completed, the engine isn't dispatched to an aircraft straight away. First, it's mounted to a test stand where real flight conditions are simulated. Once the engine passes all tests, it's disassembled, the principal components are inspected once more, and then it's assembled definitively. The finished engine is packaged and transported to a Boeing or Airbus factory where it becomes part of a new aircraft. So there you have it. Component by component, engineers create the aircraft's heart, capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Do write and let me know if you'd like to see more videos like this. Every second, the world transmits over 3 billion gigabytes of data. But do you know that all of this is thanks to a thread thinner than a human hair? And that this thread begins with ordinary sand? Not beach sand, but perfectly pure quartz, where there's only one impurity particle per million particles. To create fiber optic cable that carries light at speeds exceeding 300,000 kilometers per second, you need to journey through chemical vapors, sterile laboratories, a furnace at 2,500 degrees, and lasers that monitor every microcrack. This process looks more like manufacturing a spacecraft than a cable, but it's precisely this that forms the foundation of the internet you're using right now. To create a thread capable of transmitting light at speeds approaching 300,000 kilometers per second, you must begin with sand. But not just any sand, only special, exceptionally pure quartz sand, where the primary substance is silicon dioxide. For fiber optic production, sand with a silica content exceeding 99.9% is used, which means that in 1 million particles, only 1 particle is an impurity. Just imagine, in every kilogram of raw material, no more than a few milligrams of impurities. And this is critically important, because even a tiny particle of foreign metal can cause light scattering or absorption. And then a signal that should have traveled nearly 100 kilometers without amplification simply vanishes. Raw material for fiber optics isn't simply washed or filtered, it's purified at the molecular level. Manufacturers often employ gas chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and precipitated as the purest vapor. And only then is it converted back into glass. Add to this strict temperature control, humidity, and airflow in clean rooms, and you'll get an idea of how far removed this is from an ordinary sandy beach. Production laboratories resemble NASA's sterile zones more than a glass workshop. And all of this to ensure that every meter of future fiber contains not a single defect. A large transparent glass cylinder, which will later be melted and drawn into an extremely thin thread, is the fiber optic preform. This enormous glass blank is made using a method called vapor deposition. In a large furnace, air is mixed with extremely pure gases. These vapors reach the inner surface of a transparent tube that's heated intensely. When the vapors touch the hot wall, they settle and transform into tiny glass droplets, like dew collecting on a leaf in the morning. Gradually, these droplets accumulate layer by layer until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it closes into a dense solid rod. This is our preform. The preform is placed in a special furnace where the temperature reaches approximately 2,600 degrees Celsius. This temperature is so high that the glass becomes soft and begins to melt, like caramel on a hob. When the preform's end melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and from it forms the finest thread. This thread, the optical fiber, is drawn at speeds of roughly 300 meters per minute. Imagine, that's faster than a cyclist moving through the city. It's important that the thread has the same thickness along its entire length. Optical fiber thickness is typically around 125 microns. This is very, very thin. For comparison, the average human hair has a thickness of around 100 microns. To keep this diameter under control, special instruments are positioned in the process. They monitor the thread in real time and measure its thickness. If the thread begins to become thicker or thinner, the system automatically changes the drawing speed or furnace temperature to correct it. After the optical fiber has been drawn and has become a thin, transparent thread, it needs protection. The fiber is extremely thin and fragile. Therefore, immediately after drawing, it's coated with a special protective layer. The thin thread is drawn from the furnace. After the furnace, it immediately enters a coating machine, a special device that dresses the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. This resembles a small tube or nozzle, inside which sits molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly poured onto it. This coating layer typically consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks. The secondary coating is harder and stronger, protecting from external influences, dust, and scratches. After applying the liquid coating, the fiber passes through special forming rollers. They regulate the layer's thickness and evenness. After the polymer has been applied and formed, the fiber passes through an ultraviolet light zone. Here, under UV lamp influence, the polymer instantly hardens. This process is called polymerization. Those of you who get manicures know how this works. Ultraviolet lamps activate chemical reactions in the polymer. Thanks to this, the coating quickly becomes hard whilst maintaining its elasticity. This is an extremely rapid process. The coating hardens literally in fractions of a second. This method doesn't heat the fiber so it doesn't damage it. The entire machine is equipped with sensors and control systems. They constantly measure coating thickness and fiber feed speed. At the end of all this technological wizardry sits a spool module, rotating with a hum resembling a jet engine sound in miniature. The fiber, resembling transparent silk, lays evenly and precisely coil against coil. The spool moves smoothly left and right with millimeter precision. Around it are sensors, lasers, cameras. They vigilantly monitor that the fiber lays evenly and doesn't twist. With every minute, more and more layers appear on the spool. Imagine, in just a few hours, there are already several kilometers of the finest, almost invisible fiber. And all of this without a single break, without a single scratch. Before assembly into cable begins, fiber from the spool is carefully rewound onto the production line. Since one cable typically contains several fibers, individual threads are combined into ribbons or modules. These ribbons or bundles are then placed into buffer tubes. These are thin, flexible plastic channels that provide the fiber space for micro-movements. This is important because when temperature changes or the cable bends, the fiber slightly expands or contracts. Inside these tubes, gel may also be added that repels water and absorbs vibrations. Around the buffer tubes, reinforcing elements are added. Fiberglass or Kevlar. These are extremely strong threads that protect the cable from stretching. Metal wire is needed for additional mechanical strength. The central rod is a rigid element at the center that maintains the cable's shape. All of this is wrapped with an outer sheath. This is a dense plastic or polyethylene tube resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. Each fiber's transmission capacity is checked, along with bending strength and moisture resistance. Then it's wound onto large drums, marked, technical documents are added, and it's ready for transport and installation.
What you're witnessing here is something that would have made our grandfathers stop dead in their tracks and stare in absolute wonder. This is the forging of a massive rolling mill shaft for a steel plant weighing 5,700 pounds. That's almost 3 tons of solid steel being shaped by pure force and principles that are centuries old. The process starts with a massive steel ingot that's been heated in a gas furnace to around 2,200 degrees Fahrenheit, hot enough to glow like a miniature sun. Back in the days when American steel mills dotted the landscape from Pittsburgh to Gary, Indiana, this kind of work was the backbone of our industrial might. The forging press you're seeing here is a modern hydraulic giant capable of exerting thousands of tons of pressure. But the fundamental process hasn't changed since blacksmiths were shoeing horses on Main Street. Watch closely as the glowing workpiece gets positioned under the press. The operators, and these folks are true craftsmen, use overhead cranes and manipulators to rotate and position the workpiece with incredible precision. Every press strike, every controlled squeeze is carefully calculated. They're not just hammering hot metal, they're restructuring the grain structure of the steel, eliminating internal voids and creating a component that'll eventually face enormous forces in the rolling mill. The shaft gets worked from multiple angles, gradually taking shape. Between each pressing operation, the team repositions the workpiece, sometimes returning it to the furnace to maintain that critical working temperature. This dance between heat and pressure goes on for hours. The hydraulic press moves with deliberate force, almost gently despite its massive power. Around 5,000 to 10,000 tons of pressure compacts the steel's crystalline structure into something far stronger than the original ingot could ever be. What's fascinating is how this forged shaft will serve in a steel mill, helping shape other steel products. It's a beautiful cycle. Metal processing metal, and these shafts can last for years under extreme conditions. Today's technology, precise temperature control, computer-controlled press cycles, metallurgical analysis, ensures consistency our ancestors could only dream of. But the soul of the process remains unchanged. Heat, pressure, and the skilled hands of craftsmen who understand steel like old friends. Now here's something that combines brute force with surprising delicacy. The process of coiling a 2-inch spring bar. If you've ever wondered how these massive industrial springs are made, the ones that control freight train suspension or support heavy machinery, you're about to get a lesson. The process starts with raw stock, in this case a solid 2-inch diameter rod of heat-treated spring steel. This isn't ordinary metal. It's been precisely engineered to have the exact balance of hardness and flexibility. Too hard, and it'll snap like a pretzel. Too soft, and it won't spring back properly. Watch as the rod feeds into the coiling machine. The machine grabs one end, while a massive rotating mandrel, essentially a former, begins bending the rod around its circumference. The force required here is substantial. We're talking about permanently deforming 2-inch steel, which demands hydraulic power in the range of several hundred tons. The mandrel size determines the spring's inner diameter, and precision here is critical. As the coiling progresses, you'll notice how smoothly the rod bends despite its thickness. This is achieved through controlled feed rates and constant pressure. The machine maintains tension while rotating, creating consistent spacing between coils. Back in the 30s and 40s, this kind of work was done by hand with tremendous effort, using heat and mechanical advantage. Modern CNC systems can produce springs with tolerances measured in thousandths of an inch. What you're seeing here is one of the most reliable welding processes ever developed: submerged arc welding. This technique has been joining heavy steel since the 1930s. Here's what makes this process so special. Unlike stick welding, which your grandfather might have done in his garage, or even modern semi-automatic welding, submerged arc welding happens beneath a blanket of granulated flux. This flux, which looks almost like coarse sand, performs several critical functions. It shields the molten weld pool from atmospheric contamination, prevents oxidation, and actually contributes to the chemistry of the weld itself. The setup is mesmerizing. A continuously fed wire electrode runs through the welding head, and when it strikes an arc to the base metal, it melts both the electrode wire and the parent material, creating a deeply penetrating weld. But you can't see any of this happening because it's all taking place under that protective layer of flux. The flux melts on top, forming a protective slag that operators chip off later. Watch the welding head move along the joint. It's typically automated for consistency. The process can deposit weld metal at rates that would make a stick welder cry with envy, 10 to 50 pounds per hour depending on the setup. That's why submerged arc welding is the #1 choice for welding thick sections in shipbuilding, pressure vessel fabrication, and structural steelwork. The beauty of this process lies in its depth of penetration. Submerged arc welding can achieve full penetration welds on steel up to 3/4 of an inch thick in a single pass. Now, let's look at modern hot forging, a process that's adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisanal blacksmithing. The process begins with steel blanks, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion. But within seconds, a steel blank placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit, depending on the steel grade, the blank is transferred to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. Excess material, called flash, gets squeezed out around the edges and is later trimmed off. What's remarkable is the speed and precision of modern forging presses, machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. Sometimes you need to bend metal that's so big it seems almost impossible, and that's exactly what a horizontal bending press specializes in, forming massive pipes that can be several feet in diameter. The problem with bending large pipes is avoiding what we call wrinkling on the inside radius and tearing on the outside radius. The system solves this through controlled hydraulic pressure applied by a precisely formed die that supports the pipe during the bending process. Watch as the massive pipe gets positioned in the machine. That positioning alone requires overhead cranes and careful alignment. The bending die, often weighing several tons itself, presses against the pipe while it's supported at both ends. The hydraulic system applies hundreds of tons of force, gradually bending the pipe through the desired angle. Even with pipes this size, the bend radius, angle, and final dimensions can be controlled to surprisingly tight tolerances. These bent pipes end up in industrial piping systems, structural applications, and even shipbuilding. We're watching the cutting of a heavy railroad rail, 47 kilograms per meter, which translates to roughly 95 pounds per yard, using oxy-fuel cutting with propane. The oxy-propane torch system operates on a principle that's elegantly simple, yet demands real skill to execute properly. The propane flame, mixed with oxygen in the torch's preheat nozzles, heats a spot on the steel to ignition temperature, around 1600 degrees Fahrenheit for steel. Once that critical temperature is reached, a stream of pure oxygen under high pressure is introduced through the cutting nozzle. Here's the beautiful part. The oxygen doesn't melt the steel, it actually oxidizes it. The steel burns in the oxygen stream, and the force of that oxygen jet blows the molten iron oxide out of the cut, creating the kerf. The operator maintains a specific distance from the workpiece, the gap between the torch tip and the work surface, typically around 1/8 to 1/4 inch. Too close, and the tip will clog with splatter. Too far, and the cut becomes ragged. For cutting rail, you'll notice the torch follows the rail's profile. The rail has this characteristic mushroom shape: wide base, narrow web, and heavy head on top. Each section has different thickness, so cutting speed must be adjusted accordingly. We're now entering the realm of precision machining, where tolerances are measured in 10,000ths of an inch, and programming is just as critical as the actual technique. What you're witnessing is CNC milling of optical chuck jaws, programmed using CAM software, and this represents the perfect marriage of computer manufacturing and skilled craftsmanship. The process begins in the CAM software. A programmer working from engineering drawings creates a three-dimensional model of the chuck jaw, then generates the tool paths that will machine it. The program calculates optimal cutting strategies, selecting appropriate tools, determining feed rates and spindle speeds, and simulating the entire process virtually to catch any potential collisions or errors before a single chip is cut. Watch the CNC mill executing these programmed tool paths. This is likely a high-precision vertical machining center, equipped with a spindle that can rotate at 10,000 RPM or more while maintaining accuracy. Instead of plunging straight down, the tool follows spiral and trochoidal paths that maintain constant chip load and reduce tool wear. Notice the surface finish developing on the chuck jaw faces. These are critical contact surfaces that will grip workpieces, and they must be flat within microns and properly finished to avoid damaging delicate components. The float glass process you're watching, one of those manufacturing breakthroughs that completely transformed the industry, and remarkably, the core principle hasn't changed since it was invented back in the 1950s. Here's how this incredible process works. Molten glass, heated to around 2000 degrees Fahrenheit, flows continuously from the furnace onto the surface of a molten tin bath. The glass literally floats on the tin, spreading under gravity and surface tension, forming a ribbon with parallel surfaces and uniform thickness. Watch as the glass ribbon advances through the tin bath. Temperature is carefully controlled, gradually cooling as the glass moves forward. This controlled cooling, called annealing, is critical. It relieves internal stresses that would otherwise cause the glass to crack or shatter during cutting or installation. As the glass exits the tin bath, it's cool enough to be supported by rollers, entering what's called a layer, a long cooling tunnel where temperature continues to drop under precise control. The glass emerges at room temperature, perfectly flat with optical clarity that would have been impossible to achieve consistently using the old methods of sheet glass production. The production line can create thousands of square feet of glass daily, all with consistent quality. The ribbon is then cut to size, inspected, and prepared for further processing like tempering or coating.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands, 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end. The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go. Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood. In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry. Lead white became the foundation for paints, bright, durable, cheap. Lead coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no, lead production kept growing because a new massive application emerged: car batteries. Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70. Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste. Lead oxide gets mixed with coke and fluxes, limestone or quartz. Loaded into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal. Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid. Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off.
The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons, weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible. But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled. Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed. Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead. This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that, traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history. A metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it. Heavy, soft, toxic, but irreplaceable. This is the story of progress's dark side, how a poisonous element became the foundation of modern civilization. Every time you turn your ignition key, get an X-ray, or have a chest scan, know this: lead is working for you, shielding you from radiation, storing energy, starting engines. The paradox of a metal that kills when mishandled and saves when used right. 7,000 years alongside humanity, from ancient figurines to modern batteries. Lead is a reminder that progress always has a price, and that price is sometimes written on the periodic table with the symbol Pb, plumbum, from the Latin word meaning heaviness, the weight of choosing between toxicity and necessity. A metal humanity cannot abandon, no matter how hard it tries.
Every year, over 150 million cubic meters of plywood are produced worldwide, enough to have a train of wagons loaded with these sheets circle the Earth at the equator several times. But how is an ordinary tree trunk turned into this unique material, used in furniture, construction, and even shipbuilding? What secrets does the process hide? Starting with spa treatments for logs and ending with a hot press where layers of wood are permanently bonded into a monolith. Watch until the end and you'll learn about the secret pencil that remains after production and why it too has its own value.
It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, or pine. After delivery to the factory, the logs undergo the first and very important stage of preparation, hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours and sometimes a whole day. This kind of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible. After the bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface.
The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk like a scroll of ancient papyrus, turning a three-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer. The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor while hot air intensely blows on them from all sides. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks.
At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table, and on top of it, a sheet coated with glue. And here lies the main secret. Each subsequent sheet is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, and the third's lengthwise again. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split and evenly distributes the load. That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-story structure, between whose plates several dozen future plywood sheets are loaded simultaneously. With an enormous force reaching tens of kilograms per square centimeter, the plates compress the veneer layups. At the same time, the plates are heated to a temperature of 150 degrees Celsius. Under the influence of high pressure and temperature, the glue polymerizes, permanently bonding the layers into a single, incredibly strong monolith.
Hot sheets of plywood come out from under the press and are stacked for gradual cooling. After this, they undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, or glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a marking is applied to it. The finished stacks of plywood are sent to the warehouse to later become part of furniture, houses, and ships.
The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material. If the cylinder is massive enough, it is sent to a sawing line where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden towers.
The metal that powers the planet. Every second, 3 electric cars are sold worldwide. Every hour, 50,000 smartphones roll off production lines, and all of them depend on one element: lithium, the white gold of the 21st century. The lightest metal on Earth, which you'll never see in its pure form because it instantly explodes on contact with water. But it's what fires up your phone, drives electric vehicles, and will power humanity's future. How do salt lakes high in the Andes transform into an energy source for billions of devices? You'll discover why lithium is called white gold, how giant evaporation pools the size of a city work, and why a real geopolitical war has erupted over this metal. Watch until the end. The finale will reveal what's behind every percentage point of your smartphone's battery. This is the story of a metal that changed the world in just 20 years.
Lithium's story began in 1817 on a tiny Swedish island called Uto. A young chemist, Johann August Arfwedson, was analyzing a rare mineral called petalite when he discovered something strange. This was a metal, but incredibly light, lighter than water. Arfwedson named it lithium from the Greek word lithos, stone. Ironic, right? A stone that floats. In 1821, British chemist William Brand first isolated pure metallic lithium through electrolysis of molten salt. What he saw blew his mind. A silvery white metal so soft you could slice it with a knife like butter, and so light that a chunk of lithium actually floats on water. But that contact with water, it lasts maybe a second. Lithium instantly explodes into a violent reaction, hissing, smoking, and it can catch fire. For 150 years, lithium was just a lab curiosity. They used it in medicine to treat mental disorders, in glass and ceramic production. But everything changed in the 90s.
In 1991, Sony released the first commercial lithium-ion battery. It was a breakthrough. Before that, batteries were heavy, short-lived, drained fast. Lithium-ion batteries turned out to be 3 times lighter and held their charge way longer. The portable electronics revolution began. Cell phones became compact, laptops became light, cameras became long-lasting. But the real explosion in demand happened in the 2010s when electric vehicles hit the market. Tesla, Nissan, BMW all built their cars on lithium-ion batteries. One electric vehicle requires 130 to 175 pounds of lithium. For comparison, a smartphone contains just 1/10 of an ounce. Demand for lithium jumped from 30,000 tons in 2010 to 550,000 tons in 2023, and that's just the beginning. Forecasts predict 3 million tons by 2030. Lithium transformed from a rare lab element into a strategic resource more important than oil. But where do you get that much lithium? On Earth, lithium isn't rare. It's the 33rd most abundant element. But here's the thing. Concentrated deposits, not so common. There are 2 main sources, hard rock and salt brines. Hard rock means spodumene, a rare mineral mined in Australia, Canada, Zimbabwe. But the future? It's in the brines. High up in the salt lakes of South America, at 10 to 13,000 feet above sea level, lie the planet's largest lithium reserves. It's called the Lithium Triangle: Bolivia, Chile, and Argentina. Bolivia's Salar de Uyuni is the biggest salt flat on Earth. 4,000 square miles of blinding white salt under an endless sky. Looks like a massive frozen lake. Beneath that salt crust, brine, containing about 9 million tons of lithium. That's half the world's reserves. Chile's Atacama, the driest desert on the planet. Here too, massive lithium deposits hide in underground brines. Now, let's break down how lithium is actually extracted from these salt licks. The process looks almost magical. First, they drill wells anywhere from 65 to 330 feet deep. Powerful pumps suck up brine from these wells, a salty liquid similar to seawater, but way more concentrated. A single liter of this brine contains anywhere from 300 to 1,500 milligrams of lithium. For comparison, seawater has just 0.17 milligrams per liter. The pumped brine gets channeled into massive evaporation ponds. Picture this, artificial lakes covering dozens of hectares. From above, they look like giant colored squares, blue, turquoise, green, yellow. The color depends on mineral concentration and microorganisms. These ponds are arranged in a cascade, like giant steps. The brine flows from one pond to the next, and at each step, the magic of evaporation happens. Under the scorching sun of the high-altitude desert and relentless winds, the water evaporates, slowly, month after month. The Atacama receives less than a millimeter of rainfall per year, but the sun shines 300 days a year, perfect conditions for evaporation. The lithium concentration in the brine gradually increases. First, unwanted salts precipitate out of the solution, sodium chloride, sulfates. They're collected and removed. The process takes 12 to 18 months. Yeah, you heard that right, over a year just waiting for the sun to do its work. During this time, the lithium concentration grows by roughly 20 times. What started as a weak brine transforms into a thick, oily solution containing about 6% lithium. The brine turns amber yellow, almost like honey. It's pumped into specialized tanks and shipped to a chemical plant. Here begins the final stage of transforming salt water into white gold. At the plant, concentrated brine is treated with sodium carbonate, basically baking soda. A chemical reaction happens and a white precipitate crashes out of solution, lithium carbonate. It's not the metal yet, but it's a crucial compound. The precipitate gets filtered, washed, dried. What you end up with are fine white crystals, like powdered sugar. That's why lithium's called white gold. It actually is white. Lithium carbonate gets bagged up and shipped all over the world. Most of it goes to China, Japan, South Korea, wherever batteries are made. But that's not the end of the road. To make batteries, you need lithium hydroxide. Lithium carbonate gets dissolved in water, treated with calcium hydroxide. You get a solution of lithium hydroxide, which then gets evaporated. What remains are white crystals of lithium hydroxide, the final product, ready for manufacturing battery cathodes. The whole cycle, from pumping brine to getting the finished product, takes about 2 years. There's another method for extracting lithium, from hard rock deposits. In Australia and China, they mine spodumene, a mineral that contains lithium. They blast the rock, crush it, grind it into dust. Then they heat it to 1900 degrees Fahrenheit in massive rotating kilns. At that temperature, the spodumene changes its structure, becomes more reactive. The roasted rock gets mixed with sulfuric acid. A violent reaction kicks off, releasing heat and toxic gases. The lithium moves into a lithium sulfate solution. This solution gets purified of impurities, treated with sodium carbonate. Lithium carbonate precipitates out, the same product as from the brines. But this method is way more energy intensive and expensive. You need high temperatures, massive volumes of chemicals, tons of waste gets generated. That's why the future belongs to brines. Even though right now about 60% of the world's lithium comes from hard rock, the balance is gradually shifting towards salt lakes.
Now let's look at where all this extracted lithium goes. 75% of global production goes into batteries. A lithium-ion battery is a complex device. Inside are 2 electrodes, a cathode made of lithium oxide with cobalt or manganese, and an anode made of graphite.
Between them is an electrolyte containing lithium salts. During charging, lithium ions move from the cathode to the anode and slide between the graphite layers. During discharge, they move back, and this flow creates an electrical current. Brilliant simplicity. Lithium is ideal for this because it's the lightest metal capable of giving up electrons. A single lithium atom weighs just 7 atomic units. For comparison, lead weighs 207. That's why lithium batteries are so light and energy-dense. A modern Tesla Model 3 electric vehicle contains about 24 pounds of pure lithium in its 1,060-pound battery. This battery can travel over 300 miles on a single charge.
Beyond batteries, lithium is used in ceramics and glass production. It lowers melting temperatures and makes materials stronger. In metallurgy, lithium gets added to aluminum alloys, makes them lighter and tougher. In nuclear power, lithium produces tritium. In medicine, lithium carbonate is still used to treat bipolar disorder, stabilizes mood. Global lithium production in 2023 hit around 130,000 tons of pure metal equivalent. The major producers, Australia, 40%, Chile, 25%, China, 14%. Lithium prices rocketed from $5,000 per ton in 2020 to $80,000 in 2022, then crashed to $30,000. The market's volatile because demand is growing faster than supply. A real geopolitical battle has erupted over lithium. China's buying up deposits worldwide. The US is trying to build its own supply chain. Europe's hunting for alternative sources.
And just like that, having journeyed from salt lakes high in the Andes through 18 months of evaporation under the merciless desert sun, through chemical plants and the most complex purification processes, lithium emerges into the world, the white gold of the 21st century, the lightest metal that powers modern civilization. This is the story of how humanity learned to turn salt water from ancient lakes into energy for billions of devices. Every time you charge your smartphone, get into an electric vehicle, or fire up your laptop, remember, inside beats a heart made of lithium, the metal for which we mine deserts and drain salt flats. The metal behind the energy revolution and the move away from oil. The metal without which the future of humanity is unimaginable. White gold extracted from snow-white salt lakes to power the planet with the energy of tomorrow. Lithium isn't just an element on the periodic table. It's the key to a future that's already here.
Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears. Yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory, this is a laboratory of precision at the edge of what's physically possible. The process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace, and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine, a 100-foot-long monster. Here's where the magic happens. Liquid metal at 1300 degrees turns solid in seconds. This is continuous casting. Molten aluminum pours between two rotating water-cooled rolls, 6 feet across. Inside those rolls, water circulates at 150 pounds per square inch. When scorching aluminum hits cold steel, instant crystallization. The sound? Like dumping a bucket of water on a blazing stovetop. Hissing, crackling, clouds of steam. Out from under the rolls comes an aluminum ribbon, 1/3 of an inch thick, 5 feet wide. It's still glowing dull red, around 750 degrees. The ribbon crawls forward at 10 feet per minute, slowly cooling in the open air. I step closer and watch as a distinctive pattern emerges across the metal surface. That's the crystalline structure of aluminum. Metallurgists call this grain. Everything depends on the size and shape of those grains, how well the foil will stretch, whether it'll tear during winding, how it'll behave under heat. The perfect grain is a labyrinth, Jean-Pierre explains. The crystals need to interlock with each other, creating a strong network. If the grain's too coarse, the metal becomes brittle. Too fine, it loses flexibility. The cooled strip winds into giant coils weighing 12 tons each. These are blanks for the next stage, hot rolling. We move to the adjacent shop, where rolling mills stand as tall as a 2-story building. Here they start rolling the aluminum strip like dough, except instead of a rolling pin, 50-ton steel rollers, and instead of a table, an alloyed steel frame 3 feet thick. They feed the coil into the mill. The rollers spin, grip the strip, and pull it through with monstrous force. Pressure hits 1,200 tons per square meter. The metal resists, springs back, but gradually gives in. After the first pass, thickness drops from 8 millimeters to 4. After the second, down to 2. Speed builds. If at first the strip crawled at 5 meters per minute, after the third pass it's flying at 300 meters per minute. Air whistles. The strip hums like a taut string. Each pass generates massive heat. Metal grinding against steel heats the strip to 250 degrees. So the rollers get continuous cooling emulsion, a water oil mix. It sprays at 30 atmospheres of pressure, forming a white cloud of mist through which the strip shoots like silver lightning. After hot rolling, the strip, now 0.12 inches thick, heads to annealing. This step is critical. Here's why. During rolling, aluminum work hardens. It gets tough and brittle. The metal's crystal lattice deforms. Internal stresses build up. Keep rolling without annealing. The strip just tears. The annealing furnace is a tunnel 260 feet long. The strip travels through at 33 feet per minute. Inside, the temperature hits 930 degrees Fahrenheit in a nitrogen atmosphere. Oxygen is completely excluded. Otherwise, the aluminum oxidizes and gets covered in loose black scale. At that temperature, recrystallization happens. The metal's deformed grains heal. Internal stresses release. The aluminum goes soft and ductile again. This process takes 2 hours. Coming out of the furnace, the strip cools in a water bath, then gets dried with hot air. Now it's ready for the most demanding stage, cold rolling to final thickness. The cold rolling mill, that's the heart of the factory. 3 state-of-the-art rolling stands here, capable of rolling aluminum down to 6 microns thick. That's the limit. Any thinner? Physically impossible without tearing. The process takes 20 passes. Each pass reduces thickness by roughly 30%. 0.12 inches becomes 0.08, then 0.06, then 0.04, and so on, until you hit 0.0024 inches, 6 microns. Rolling speed on the final passes? 67 miles per hour. The foil ribbon flies faster than a car on the highway. The slightest vibration, the tiniest roller deviation, and it tears. A tear at that speed means shutting down the entire line, losing several tons of material and hours of rethreading. That's why laser thickness gauges are installed here, measuring the strip 200 times per second, accurate to 0.4 microns. The computer instantly corrects roller pressure, rolling speed, coolant flow. A human? Couldn't react fast enough. I'm watching the monitor in the control room. The thickness graph runs flat, 6.0 microns, 6.1, 6.0. Deviation within plus or minus 0.8 microns. That's perfection. But there's a problem. You can't roll foil 6 microns thick in a single pass. It sticks to itself, tears, crumples. So they use a clever trick, doubling. 2 layers of foil, each 12 microns thick, are stacked together and rolled as one. The rollers press down, and both layers simultaneously thin to 6 microns. But between them remains the thinnest air gap. After rolling, the layers are separated. And here's where an interesting effect shows up. One side of the foil, the one that contacted the roller, comes out, shiny, mirror-like. The other side, which contacted the neighboring foil layer, stays matte. You've probably noticed this on kitchen foil. Well, it's not a defect and not a special coating. It's the trace of the doubling process. The matte side is the imprint of the microtexture from the adjacent sheet. At the molecular level, it's covered with microscopic irregularities that scatter light. The finished foil gets wound onto huge jumbo rolls, 6.5 feet across and weighing 3 tons. These are the mother rolls. From them, they'll later cut foil to the needed width. For chocolate wrapping, 12 inches; for yogurt lids, 2 inches; for industrial uses, 4 feet. Quality control at Eurofoil borders on paranoia. And that's a good thing. Every jumbo roll goes through a dozen tests. First up, backlighting. The foil passes in front of a powerful lamp. Any microcrack, any pore, and light will shine through. A computer flags the defect, and that section gets marked as scrap. Second, leak testing. A foil sample gets clamped between 2 chambers. Helium under pressure is fed into one. A highly sensitive detector sits in the other. If even a single helium molecule seeps through the foil, test failed. Third, mechanical testing. The foil is stretched on a specialized machine, measuring tensile strength. Quality foil must withstand a load of at least 15 megapascals. That's roughly 330 pounds per square inch. For a material 6 microns thick, that's a phenomenal number. Fourth, chemical analysis. Every 2 hours, they take a sample and run it through a spectrometer. It shows the exact alloy composition down to hundredths of a percent. Any deviation, and the batch goes back to the smelter. Fifth, corrosion testing. A sample is held in salt fog at 95 degrees Fahrenheit for 72 hours, simulating 3 years of use. If corrosion shows up, it's scrap. The final stage, slitting and packaging. Jumbo rolls feed into slitter rewinders. Disc blades made from hardened steel, sharpened to razor-edge sharpness, cut the 10-foot wide web into narrow strips of the required width. Slitting speed, 1,600 feet per minute. Blades spin at 3,000 revolutions per minute. The slightest wobble, and the foil edge comes out ragged, jagged. That's why blades get swapped every 8 hours. Slit rolls move to winding. Here the foil winds onto cardboard cores 3 inches in diameter. For household foil, the standard, 33 feet per roll. For the food industry, rolls of 1,000 feet, 1,600 feet, 3,000 feet. An automatic system measures the required length, cuts, seals the edge, marks the roll with a barcode. Output, 200 rolls per minute. Finished rolls get packed into cardboard boxes, boxes loaded onto pallets, pallets hauled to the warehouse. From here, Eurofoil foil ships to 70 countries worldwide. To Germany for chocolate wrapping, to France for cheese factories, to Italy for coffee capsules, to Switzerland for pharmaceutical blister packs, to Japan for electrolytic capacitors. I'm standing in a finished goods warehouse. Around me, stacks of pallets tower 13 feet high. Each pallet holds 2,000 rolls of household foil or 50 jumbo rolls of industrial grade. The product stored here is worth around 5 million euros. The plant runs at full capacity. 100 tons of foil per day, 3,000 tons per month, 36,000 tons per year. That's enough material to wrap the entire United Kingdom in a continuous sheet, or package 15 billion chocolate bars, or make 300 billion yogurt lids. This entire foil empire was born from a simple piece of aluminum that passed through the inferno of casting furnaces, the monstrous pressure of rolling mills, the precision of laser measurements, and rigorous quality control. From 8 millimeters down to 6 microns, a journey 1,300 times over. If you found it interesting to learn how a material thinner than a human hair but stronger than many plastics is created, hit the like button on this video. Write in the comments whether you knew that aluminum foil can be recycled infinitely. And subscribe to the channel to keep discovering the technologies that surround us every day but remain invisible.
Every year, the world produces billions of square feet of veneer, a petal-thin material hiding the strength and beauty of entire forests. Picture this. From a single log, you can get enough surface area to cover a football field. That's exactly why this industry is worth over $40 billion annually. From one perfect American walnut log, about 3 feet in diameter, you get anywhere from 10,000 to 30,000 square feet of unique surface. One log, almost an entire football field of veneer. Using veneer cuts the need to harvest valuable tree species by 98% compared to making furniture from solid wood. Instead of cutting down 20 trees to make 20 tables, you can harvest one perfect tree and leave the other 19 growing in the forest. But what's behind that number? How does an ordinary tree go through spa treatments, fiery tunnels, and encounters with scalpel-sharp blades to become luxury furniture? Watch closely. At the end, you'll discover a secret almost nobody realizes. Picture a lumber mill that specializes in veneer production. Massive logs of premium hardwoods, oak, ash, maple, walnut, cherry, arrive here by truck. But not every tree makes the cut. These have to be perfectly straight, tall trees with large trunk diameters, and most importantly, free of knots, cracks, and other defects for a significant height. Every knot is a scar that ruins the perfect grain pattern. That's why only the finest specimens are chosen for veneer. When one of these perfect logs arrives at the mill, it doesn't go straight to the blade. First, it gets the industrial spa treatment. The logs are submerged in enormous pools of hot water or placed in special chambers filled with hot steam. This isn't about cleanliness. This process, lasting anywhere from several hours to several days, at temperatures around 212 degrees Fahrenheit, does two crucial things. It softens the wood, making it more pliable and cooperative for cutting, and it transforms its color, making it richer and more uniform. After the hot bath, the bark gets stripped from the log. A special machine peels away the rough outer shell, revealing clean wood underneath. And now comes the most critical moment before the main show, centering. The log gets locked into the machine, and an operator uses lasers to find its perfect axis of rotation. This is absolutely crucial. Giant pencil in a giant sharpener. The log starts spinning around its axis, and the blade cuts into the spinning wood and starts shaving off a continuous wide ribbon of veneer, just 1/50th to 1/8 of an inch thick. It's like unrolling a paper towel roll. An endless, wet, flexible sheet comes out of the machine, which is then cut into pieces of the right size. This method is highly productive, but it creates a characteristic chaotic pattern that isn't always valued in high-end furniture. The second method, used to obtain the most beautiful decorative veneer, is called slicing. This isn't a sharpener anymore. It's the world's biggest cheese slicer. Here, a log, or part of it cut into beams, is firmly secured to a movable platform. Above it, or to the side, sits a massive, sharp blade. The platform with the wood moves back and forth, or up and down, and with each pass, the blade shaves off a single, perfectly flat sheet of veneer. It's a slower, less productive process, but it's what gives you that refined, linear, or figured grain pattern we value so much in expensive furniture. Depending on exactly how the log was cut before slicing, you can get different types of patterns: radial, tangential, mimicking the look of solid plank. Freshly cut veneer, no matter the method, is called green. It's soaking wet, flexible like damp paper, and tears easily. It needs to dry. The ribbons or sheets of veneer are carefully fed into a long drying chamber. Think of it as a giant tunnel oven, where the veneer slowly moves along on rollers or a mesh conveyor. Hot air circulates inside, gently and evenly pulling moisture out. The process is tightly controlled. Dry it too fast and the veneer will crack or buckle. Within minutes, that wet, floppy sheet becomes dry, slightly brittle but stable. After drying, the veneer sheets have ragged edges. They're stacked high and sent under a massive guillotine. A sharp blade slams down and in one stroke slices off the rough bits, creating perfectly straight edges. Now the sheets are ready for the most critical stage, where it's not machines doing the work, it's people with trained eyes. This is sorting. Specialists carefully inspect each sheet, evaluating its color, grain pattern, and any defects, then sort them into bundles by grade. It's meticulous work, because this determines the veneer's price and application. But individual veneer sheets are often too narrow for making something like a tabletop, so they need to be joined into one large panel. This process is called stitching or splicing. Two sheets with perfectly straight edges are fed into a special machine.
It presses them tightly together, and a specialized mechanism bonds them. This could be a thin zigzag line of adhesive or a glued paper tape. The result? A large, continuous veneer sheet, ready to be applied to a substrate. Now for some history. Using thin layers of wood goes back thousands of years. Ancient Egyptians used veneer to decorate sarcophagi and furniture 3,000 years ago. But modern industrial veneer production only began in the 19th century with the invention of steam engines and precision machinery. The first veneer peeling lathes appeared in the mid-19th century and revolutionized the furniture industry. Instead of sawing valuable wood species into thick boards and losing most of the material to sawdust, manufacturers could now obtain ultra-thin sheets, maximizing every inch of the log. The global veneer market is a massive industry, turning over more than $40 billion a year. The largest producers are China, the US, Germany, Italy, and Indonesia. Veneer isn't just for furniture. It's used in making doors, musical instruments, yacht interiors, luxury car interiors, and premium space finishes. But the most important application is plywood. Yes, ordinary plywood as we know it is multiple layers of veneer glued together with perpendicular grain direction. This exact structure gives plywood its strength and resistance to warping. And now the most impressive number behind veneer, its efficiency rating.
Take one massive, perfectly straight log of premium American walnut, several yards long and about 3 feet across. If you just sawed it into boards, you could make, say, one big table and a few chairs. Now here's the kicker. If you slice that same log into veneer just 24 thousandths of an inch thick, you can get anywhere from 10,000 to 30,000 square feet of unique surface. To put that in perspective, that's enough to cover almost an entire football field from a single log. Using veneer cuts the need to harvest precious hardwoods by 98% compared to making solid wood furniture. Meaning instead of cutting down 20 trees to build 20 tables, we can harvest one perfect tree and leave the other 19 growing in the forest. This makes veneer one of the most environmentally responsible ways to use wood. But veneer has another hidden advantage that few people think about. The thing is, the most beautiful, unique wood grain patterns are often found in the most unusual parts of a tree, where the trunk branches out, in burls, in the root section. If you saw a tree like that into boards, these areas often end up as scrap because they're too small or irregularly shaped. But with veneer production, even a small section with a unique pattern can be turned into several square meters of luxurious material. There are entire categories of exclusive veneer made from burls, wood growths with incredibly complex, swirling patterns. One burl the size of a soccer ball can yield enough veneer to finish an entire study, and this veneer can cost thousands of dollars per square meter. There's even a market for archive veneer, material made from trees cut down decades or even centuries ago and stored in warehouses. Some species of wood that are now protected or extinct can only be found in the form of this archive veneer. Veneer manufacturing technology is constantly evolving. Modern machines are equipped with laser scanning systems that analyze the log structure before cutting and select the optimal angle and method to produce the most beautiful grain pattern.
Computer control allows sheets less than half a millimeter thick to be sliced with precision down to hundredths of an inch. New processing methods are being developed that enable veneer to be stained, embossed with textures, and made to imitate rare species. And so, after journeying from a majestic tree in the forest through a hot bath at 200 degrees Fahrenheit, past a knife sharp as a scalpel, and through the fiery tunnel of a dryer, this material emerges, thin as a petal, carrying all the beauty, history, and unique character of the forest, ready to bring a piece of it into our homes. These billions of dollars aren't just money, they're proof that beauty and practicality can walk hand in hand, allowing us to enjoy nature's unique patterns without causing irreparable harm. Every sheet of veneer is a thin slice of a tree's history, one that lived for decades or centuries and is now ready to serve humanity for centuries more in the form of beautiful furniture.
Every year, enough glass fiber rebar is produced worldwide to challenge the dominance of steel itself. This isn't science fiction, it's modern manufacturing. The world spends billions fighting rust, repairing bridges and car parks destroyed by corrosion. But there is a solution. A composite material that is twice as strong as steel, 4 times lighter, and simply does not know the meaning of the word rust. The market for this material is growing at 12% a year, and today you will see how hundreds of bobbins and a barrel of resin give birth to the building material of the future.
It all begins at one end of a vast workshop, in front of a structure that looks like a giant library for thread. It's called a creel. On a wall several meters high, hundreds, sometimes thousands of huge bobbins are mounted in neat rows. Wound onto each one is a fine glass thread, or roving. This isn't the glass from your windows. It's a special glass fiber produced by melting glass and drawing it through microscopic holes. The result is a thread thinner than a human hair, but with incredible tensile strength. This will be the skeleton. From each of these hundreds of bobbins, a single separate thread is drawn, and they all converge into one thick, fluffy bundle.
This river of glass fiber now begins its journey. It passes through a system of guides and tensioners. Each of the thousands of threads must be held at exactly the same tension. If one thread sags while another is too tight, the load in the final product will be distributed unevenly, compromising its strength. The dry glass bundle is then slowly submerged in a bath filled with a thick, sticky, honey-like liquid. This is the polymer resin, the flesh that will be built upon the glass skeleton. It's a complex chemical cocktail. The base is typically a polyester, vinyl ester, or epoxy resin. To this, a hardener is added, a catalyst that will trigger a chemical reaction, turning the liquid into a solid plastic. Various additives can also be mixed in. Pigments for color, UV inhibitors to protect the rebar from sunlight, and fire retardants. The purpose of this bath is to impregnate every single tiny fiber. The bundle must be completely saturated in the resin, leaving no dry spots. Now heavy and soaked in sticky resin, the bundle emerges from the bath and heads towards the point of its creation, the forming die. This is the heart of the entire process. Imagine a thick steel plate with the perfectly round, polished hole, its diameter precisely matching that of the future rebar. The die is heated to a specific temperature. As the wet bundle is pulled into this hole, several things happen at once. First, the die acts like a press, squeezing out all excess resin. Second, it compacts all the glass fibers tightly together, forming a perfectly round rod. Third, the heat from the die initiates the first stage of the curing reaction. Emerging from the die, we can already see the familiar shape of a rebar, but it is still soft and vulnerable. So how does it get its famous ribbed surface? Immediately after the die, while the rod is still hot and pliable, a special glass fiber strand is wound around it. A thin resin-soaked thread is wrapped in a spiral around the surface of the rod, creating the textured pattern. The formed and wrapped rod now enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber which can stretch for dozens of meters, where a high temperature, typically around 200 degrees Celsius, is maintained. Here, the final transformation occurs. This isn't just drying. Under the heat, the resin molecules begin to rapidly link together, forming a strong, rigid, three-dimensional grid. The liquid, sticky syrup turns into an exceptionally strong and hard composite material, permanently bonding millions of glass fibers into a single, monolithic rod. As the rebar moves slowly through this hot tunnel, it acquires its final, rock-hard strength.
But what is pulling it through this long journey? At the end of the line sits a special pulling device. It typically consists of two caterpillar-tracked mechanisms like those on a tank, positioned one above the other. They gently, but very firmly, grip the finished solid rebar and pull it towards them at a constant, precisely controlled speed. It is this machine that provides the force to draw the glass fibers through the resin bath, the forming die, and the oven. The speed of this movement is one of the most critical parameters controlling the quality of the final product. And so, from the other end of this long production line, an endless, perfectly straight, hard and hot GFRP rod emerges.
The final act is cutting. An automatic saw is mounted across the line. It synchronizes with the speed of the moving rebar, and at the right moment, it makes a quick forward dash, and with a sharp whiz, it cuts a standard length, for example 6 or 12 meters, from the continuous rod. It then returns to its starting position. The finished, still warm rebars roll onto a cooling table, after which they are collected into bundles, tied, and sent to the warehouse. And so, before our very eyes, thousands of fragile glass threads and a barrel of sticky liquid have journeyed through baths, presses, and ovens to become the lightweight yet incredibly strong building material of the future.
The market for glass fiber rebar isn't yet a giant like the steel market, but it is the boldest newcomer, rapidly gaining traction. The global market for this material is already valued in the hundreds of millions of dollars, with staggering forecasts. It's expected to grow by 10 to 12% annually. Now for the key features that are making the steel industry nervous. The first and most obvious is weight. GFRP rebar is roughly 4 times lighter than steel of the same diameter. Imagine a lorry. It can deliver 4 times more GFRP rebar in a single trip than it could steel.
On the construction site, two workers can easily carry entire coils of GFRP rods, whereas moving steel requires a crane. This represents a colossal saving in logistics and labor. Second is strength. And here, GFRP steps into the ring and knocks steel out in the first round. Its tensile strength is approximately twice that of standard steel rebar. This means that for some structures, a smaller diameter rebar can be used, saving even more on weight and volume.
But the ultimate advantage, the true superpower of GFRP, is its war on rust. The main enemy of any reinforced concrete structure, from bridges to car parks, is not the load, it's rust. Water and salts penetrate through microcracks in the concrete, reach the steel rebar, and it begins to corrode. Rust expands in volume and literally bursts the concrete from within. And GFRP? It simply laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means the lifespan of the structure increases dramatically. A concrete structure reinforced with steel is designed for about 50 years. A structure with GFRP rebar can easily be designed for a lifespan of over 100 years.
What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, then gets reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore flare up like tiny controlled earthquakes. Zinc, the fourth most consumed metal in the world after iron, aluminum, and copper. 12 to 13 million tons of zinc are produced every year. 60% of all zinc goes into galvanizing steel. Without it, bridges, cars, and buildings would rust many times faster. But here's the shocker. At 2,700 degrees Fahrenheit, zinc literally turns into vapor and disappears into the air, and then condenses back into liquid metal. In this video, you'll learn things you never suspected, and at the end, the main secret will be revealed that will forever change how you think about zinc.
Picture a massive underground mine somewhere in China, Australia, or Peru, the world's biggest zinc producers. These are entire underground cities stretching hundreds of feet, sometimes even miles beneath the Earth's surface. We're not talking about simple holes in the ground. This is a network of tunnels, shafts, ventilation systems, and lift shafts. Powerful drilling rigs bore holes into the rock, blast holes. Explosives get packed into these holes. After a carefully controlled blast, massive volumes of rock break apart. It's like a spectacular but controlled earthquake in miniature. Dusty air gets quickly cleared by powerful ventilation systems, which also pump fresh air down to these depths. The broken ore then gets loaded onto massive underground trucks or conveyor belts using front-end loaders. It's a genuine underground transportation flow, continuously moving, hauling tons of ore to the central lift shafts. From there, the ore rises to the surface using powerful elevators or specialized conveyor systems, climbing hundreds of feet straight up. At every stage, from drilling to hoisting, Strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock, containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a concentrator plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore enter crushers that, with a deafening roar, break them down into smaller pieces. Then this crushed ore moves into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore is ground down to an extremely fine powder, almost like flour. This is critically important to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder is mixed with water and special chemical reagents in large tanks called flotation cells.
These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. The zinc mineral particles latch onto these bubbles and rise to the surface, forming foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can contain up to 60% zinc. Since zinc is often found alongside lead, the processing plant may run multiple flotation cycles to separately extract zinc concentrate from lead concentrate. The zinc concentrate you end up with still isn't pure metal. It has to go through metallurgical processing to get metallic zinc. And now we enter the world of extreme temperatures. If the pyrometallurgical method is used, the zinc concentrate first undergoes roasting. The concentrate is heated in specialized furnaces at temperatures around 1800 degrees Fahrenheit.
This removes the sulfur, which is part of the sulfide ore, converting it into zinc oxide. The sulfur transforms into sulfur dioxide gas, which is captured and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable product. Next, the zinc oxide is mixed with coal and heated to even higher temperatures, over 2200 degrees Fahrenheit, sometimes even 2700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process occurs. The carbon strips oxygen away from the zinc oxide, freeing up pure metallic zinc. And this is where that incredible wow moment of vaporization happens. At these temperatures, the metallic zinc transitions into a gaseous state. It evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is significantly higher, zinc literally turns into vapor, which rises and gets collected in specialized condensers.
The vapor cools and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or granules. Now for the history. Zinc has been known to humanity for thousands of years, though it was only isolated as a distinct metal in the 16th century. Ancient civilizations used brass, an alloy of copper and zinc, without knowing it actually contains zinc. In India and China, people learned to smelt zinc as far back as the Middle Ages. But modern industrial zinc production only began in the 19th century with advances in smelting technology. The primary use of zinc: galvanizing steel. Around 60% of all zinc produced goes toward protecting steel from corrosion. Zinc coating on steel creates a sacrificial layer. The zinc oxidizes instead of the iron, protecting the structure. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a surge in resource demand.
15 to 20% of zinc goes into making alloys like brass and die casting alloys. These alloys end up in car parts, home appliances, toys, plumbing, and electronics. Another 10 to 15% becomes zinc oxide and other chemical compounds. Zinc oxide has crazy wide applications: sunscreens and cosmetics, paints, ceramics, rubber manufacturing, and even livestock feed supplements. Its antibacterial and protective properties make it a universal ingredient. The rest of the zinc gets used in batteries, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, because zinc is absolutely vital for the human immune system. As for prices, like most commodities, zinc prices swing with global supply and demand, economic cycles, and what's happening in the biggest producer and consumer countries.
Yet demand for zinc remains steady or growing, driven by urbanization, infrastructure development, and the need to protect metals from corrosion worldwide. This makes zinc a crucial indicator of global economic health. Zinc ranks as the fourth most consumed metal on the planet, after iron, aluminum, and copper. That alone tells you just how massive its importance is for the global economy and industry. Annual worldwide zinc production sits at roughly 12 to 13 million metric tons. These are enormous volumes, underscoring its irreplaceability across hundreds of applications. The primary zinc mining regions are China, Australia, and Peru. These three countries together account for a significant share of global zinc ore extraction, making them key players in the market. For instance, China isn't just the largest producer, it's also the world's biggest zinc consumer, reflecting its powerful industrial expansion. Other major producers include India, the United States, Mexico, and Canada.
When it comes to reserves, the U.S. Geological Survey estimates global zinc reserves at roughly 250 million metric tons. On top of that, there are what's called resource spaces, potential deposits that haven't been explored yet or aren't economically viable to mine right now. Those are estimated at over 1,800 million tons. These numbers show that zinc, unlike some rare metals, will last for many decades, even with growing consumption. Most zinc is mined from underground operations, entire subterranean cities stretching hundreds of feet, sometimes several miles beneath the Earth's surface. These aren't just holes in the ground, they're networks of tunnels, shafts, ventilation systems, and hoisting shafts. It all starts with exploration. Geologists, like detectives, hunt for ore bodies, sections of rock where the concentration of zinc, which, by the way, usually occurs as sulfide ore, like sphalerite, and almost always comes with lead, silver, and sometimes copper, is high enough to make it worthwhile. Once a deposit is discovered, mine construction begins. This involves sinking vertical shafts, which provide access to the ore, lift materials up, lower equipment down, and creating horizontal tunnels, or drifts, that lead directly to the ore veins. The actual ore extraction process? Dynamic, risky. Miners use specialized equipment, powerful drilling rigs that bore holes into the rock, called blast holes. Explosives get packed into these holes. After a carefully controlled detonation, massive volumes of rock shatter. It's like a spectacular earthquake, in miniature, under control. And that's how, starting from an underground explosion, through crushing into powder, through flotation with millions of tiny bubbles, through roasting at 1800 degrees and reduction at 2700 degrees, where the metal literally turns into vapor and vanishes into thin air, then condenses back into liquid zinc, a metal is born that shields steel from rust, makes bridges possible, cars, skyscrapers, without which the modern world would look completely different.
You believe that in the United States alone, the electrical wire industry pulls in tens of billions of dollars in revenue every single year? These seemingly small spools of wire carry the entire flow of energy that keeps modern civilization running. Behind every foot of wire lies rigorous engineering. Copper is drawn through a series of steel dies to hit precise dimensions, then coated with layers of insulation designed to withstand heat and resist moisture. A deviation of just a few thousandths of an inch can lead to overheating, short circuits, and serious safety hazards. In this documentary, we're going inside the manufacturing process of electrical wire, the invisible foundation of modern life. From a thin strand of metal that seems almost fragile, electrical wire becomes the silent foundation of modern life. At a diameter of just about 0.08 inches, a single copper conductor can carry enough current to light up an entire house. Inside its thin insulation layer flows a constant stream of energy, transforming invisible motion into light, heat, and the continuous operation of the world around us. And when its mission is complete, electrical wire doesn't reach the end of its life. Copper can be reborn almost infinitely. The plastic insulation is stripped away, the metal is cleaned, melted down, and drawn again into new wire. Each recycling cycle consumes far less energy than mining and refining new ore, reducing waste and preserving natural resources. It's a closed loop, where technology and sustainability coexist in something as small and unassuming as a single wire. The journey of an electrical wire begins deep underground, in massive copper mines, where the red metal is extracted from ancient layers of rock. Copper ore doesn't exist in pure form. It's locked tight inside stone, soil, and mineral compounds. To reach it, people must drill, blast, and remove layer after layer of geology, hauling thousands of tons of rock to the surface every single day to recover just a tiny amount of copper. On average, producing a single pound of refined copper requires processing anywhere from 200 to 1,000 pounds of raw ore, depending on the metal content in each deposit. This shows that copper's value comes not from abundance, but from the precision required to extract it from an enormous mass of material. Most modern copper mines are giant, open-pit operations, hundreds of feet deep and miles wide. Seen from above, they look like colossal funnels carved into the Earth's surface. Every day, hundreds of ultra-heavy dump trucks, each hauling over 300 tons of rock, move continuously between the pit and the processing facilities. Once ore leaves the mine, it's still nothing more than solid rock with metal locked inside. To reach the copper, the first critical step is primary crushing, breaking down the rock's structure and freeing up the mineral particles. At the crushing plant, ore gets reduced through multiple stages, from large rocks to gravel and finally into a fine powder. The finer it becomes, the more efficiently copper-bearing minerals separate from the surrounding waste rock, preparing the material for the next stage of separation and concentration. Then the powdered ore goes into the flotation process. Water, air, and very small amounts of chemicals combine to create countless microscopic bubbles. Copper-bearing mineral particles attach to these bubbles and rise to the surface, while the heavier, worthless rock sinks to the bottom. This is the first true separation step, where the metal begins to be recognized and isolated from the rest of nature. The result is copper concentrate, containing 25 to 35% copper, a dramatic increase from the initial 1 to 5% found in raw ore. Though this isn't pure copper yet, this concentration stage is crucial. It transforms mountains of seemingly worthless rock into a metal resource with real industrial value. After crushing and flotation, the concentrate still isn't metal. At this stage, copper remains locked inside mineral compounds and requires one decisive step to be fully liberated: smelting. The concentrate is fed into furnaces operating at extremely high temperatures, often exceeding 2,300 degrees Fahrenheit. Under this intense heat, sulfur compounds and impurities begin to break down. They burn off, vaporize, or separate into slag, while the heavier metal settles at the bottom. This is the moment when mineral ore truly transforms into metal. After smelting, the resulting copper is known as blister copper, with a purity of 98 to 99%. Its surface shows a characteristic dark red color. The metal is dense, heavy, and conducts electricity far better than any mineral form before it. From rock and powdered ore, copper emerges for the first time as an industrial metal. Once copper is in its molten metallic state, it must be shaped into a form that can be transported and further processed. Here begins the casting stage. A stream of liquid copper, glowing red like lava, is drawn from the furnace and poured into heat-resistant steel molds where the metal's shape is first controlled with precision. Within minutes, the temperature drops and the copper solidifies into dense metal blocks known as billets or ingots. After casting into rough copper plates, the metal is still not pure enough to serve as an electrical conductor. Tiny impurities remain inside, small enough to escape the eye but significant enough to reduce transmission efficiency. To meet electrical industry standards, copper must go through an almost absolute purification step: electrolytic refining. Rough copper plates are suspended in large tanks filled with electrolytic solution. When electrical current flows, the metal surface slowly dissolves. Each copper atom separates from the rough plate and moves through the solution. On the opposite side, these atoms settle on cathode plates, forming a new layer of copper that is brighter, purer, and more uniform in structure. The result is copper sheets with purity up to 99.9%, the level required for electrical power systems. After refining, high-purity copper is remelted and cast into large round rods called wire rod. These rods are about half an inch in diameter and serve as the starting point for all subsequent wire drawing processes. Wire drawing is the process of gradually pulling metal through a series of progressively narrower steel dies, each one slightly smaller than the last. When the copper rod is pulled through the first die, its diameter decreases slightly while its length increases. The process repeats through the second, third, and each subsequent die until the wire reaches the required thickness. Throughout this process, the wire is coated with a special lubricating solution to reduce friction, limit heat buildup, and protect the metal surface. Wire drawing doesn't happen in one step. It's a sequence of gradual reductions. A single wire typically passes through 10 to 30 different dies before reaching its final size. For example, from an initial diameter of about half an inch, the wire can be drawn down to around 0.08 inches, and even much smaller for electronic wires. As the copper is continuously stretched, its internal crystalline structure becomes harder and loses its natural ductility. For this reason, after a certain number of drawing passes, the wire must be lightly annealed at temperatures from 600 to 800 degrees Fahrenheit to soften the metal again. After the wire is drawn to the right size, the individual copper strands are still too thin and too stiff to be used on their own. To become the flexible, durable conducting core in real-world applications, they have to go through a twisting process. Copper strands are fed into a twisting machine, where dozens of spinning spools work simultaneously, twisting each strand around a central axis at a precisely calculated angle. This twist angle directly determines the flexibility and bend strength of the wire. A tighter twist creates a stronger, more compact core. A looser twist makes the wire more flexible. That's why every type of electrical cable, from household wiring to industrial power lines, has its own specific twist structure. A single conductor can be made from 7, 19, 37 strands, or even more. These numbers aren't chosen randomly. They follow geometric patterns that allow the small wires to fit tightly together, forming a round, uniform core with minimal empty space and even distribution of electrical current across the entire cross-section. Thanks to the twisted structure, mechanical stress is distributed among many small wires, significantly reducing the risk of cracking or metal fatigue. At the same time, microscopic gaps between the strands help dissipate heat more efficiently as electrical current passes through the conductor. Once the copper core has been fully twisted, it still can't be used safely. Bare metal conducts electricity too powerfully. Even the slightest point of contact can cause short circuits or pose serious danger to people. That's why the conductor must move to the insulation stage. The twisted core runs continuously through an extrusion system, where insulating materials like PVC, PE, or cross-linked polyethylene are melted and pressed tightly around the entire metal surface. The molten plastic flows evenly in tubular form, wrapping tightly around the copper core and forming a completely sealed layer. This becomes the protective sheath that prevents electricity from leaking and isolates the conductor from the environment. The thickness of this insulation layer is controlled with extreme precision. If it's too thin, safety is compromised. If it's too thick, the cable becomes stiff, difficult to install, and wasteful of material. For this reason, diameter sensors work continuously during extrusion, ensuring the plastic coating remains uniform along the entire length of the wire. Immediately after coating, the cable passes through a cooling system using water or air, allowing the plastic to harden quickly and hold its precise shape. Once the insulation layer has completely cooled and stabilized, the wire feeds directly into the winding machine. Before reaching the spool, it passes through a tension control system that keeps the cable in a perfectly balanced state. It can't be too loose, which could cause tangling, and it can't be too tight, which could stretch the copper core or deform the plastic insulation. The spool rotates smoothly while a lateral guide mechanism moves back and forth, laying the wire in parallel, tightly aligned loops. Each turn is placed neatly beside the previous one, building layer by layer into a uniform, perfectly formed coil. Throughout the winding process, wire length is continuously measured by sensors. When the preset number of feet is reached, the system automatically stops, cuts the wire, and secures the end of the spool. After winding, the wire moves to the packaging area for protection against dust, moisture, and physical damage. Each spool is wrapped in plastic film or shrink wrap, and larger spools are additionally secured with plastic straps or steel bands to maintain their shape. Next, technical information such as wire type, cross-section, length, voltage rating, and production date is clearly marked on the packaging. From deep copper mines beneath the Earth's surface, the red metal embarks on a long journey through science and industry to become electrical wire. Every single stage, from refining and forming to drawing, twisting, insulating, spooling, and packaging, demands extraordinarily high technical precision. What appears to be a simple product is actually the result of ancient geology, modern engineering, and a massive manufacturing system operating without pause. If you're fascinated by the hidden stories behind everyday objects, where industry and science unite to shape the world we live in, subscribe to the channel. Every video is a journey into how humanity transforms raw resources into the foundations of modern civilization. What if I told you there's a metal that's 15 times rarer on Earth than gold? And to mine just 1 ounce of it, you need to process 10 tons of ore. A metal whose entire annual supply would fit in an ordinary room, while all the gold in the world would fill 3 Olympic-sized swimming pools? Every year, the world produces only 180 tons of platinum. That's 17 times less than gold. South Africa produces 120 tons, 74% of global production. Russia's in second place with 23 tons. To extract 1 ounce of platinum requires processing 10 tons of ore, while for gold, just 2 to 3 tons. The Merensky Reef, Upper Group 2, and Platreef contain only 2 to 10 grams of platinum per ton of ore. After flotation, the concentrate is heated to 1500 degrees Celsius to burn off iron and sulfur impurities. Then they use aqua regia, a mixture of nitric and hydrochloric acids, to dissolve the platinum. The concentration of platinum in Earth's crust is only 0.5 parts per million. Stick around till the end. You'll discover a secret that even jewelers won't tell you. Picture an underground mine several miles deep somewhere in South Africa, in the Bushveld province, home to the world's largest platinum deposits. These aren't open-pit mines. They're narrow tunnels blasted through rock up to 2 miles beneath the surface. Here, platinum is extracted from thin layers, reefs, that stretch for hundreds of miles but measure just 6 inches to 5 feet thick. 3 main reefs: the Merensky Reef, Upper Group 2, and Platreef. The Merensky Reef, discovered by Hans Merensky in 1924, has historically dominated global platinum production. Here, platinum reaches its highest concentration, 50 to 60% platinum group metals. Upper Group 2, a chromite-rich reef, more stable but with lower gold, copper, and nickel content. Platreef, a wider reef with lower platinum grades but higher base metal content, roughly 5 times more. Miners drill holes into the reef walls and pack them with explosives. After detonation, the shattered rock containing platinum and other metals is transported to the surface for processing. The ore gets crushed, then goes through flotation. That's a process that separates minerals based on how they stick to air bubbles in water. Mills grind the ore down until 60% of the particles pass through 75 micrometers. Then the ground ore gets mixed with water, and collector reagents are added, things like xanthates and dithiophosphates, which make the sulfide minerals containing platinum hydrophobic. Water repelling. Air gets pumped through the mixture, creating millions of tiny bubbles. The hydrophobic particles containing platinum stick to the bubbles and rise to the surface, forming a froth that gets skimmed off. Hydrophilic waste rock particles stay at the bottom. Platinum in Merensky ores is closely tied to base metal sulfide minerals: copper, nickel, and cobalt. The platinum group metals are present either as discrete platinum group minerals included in or attached to the sulfides, or in solid solution with the sulfides. The base metal sulfide minerals in Merensky: pyrrhotite, pentlandite, chalcopyrite, and traces of pyrite. After flotation, the concentrate still contains less than 1% platinum. Now, the concentrate heads to the smelter. It's dried and then heated in electric furnaces to temperatures exceeding 2700 degrees Fahrenheit. Air is blown through the molten metal to oxidize iron and sulfur impurities. Sulfur oxidizes to sulfur dioxide and gets removed as exhaust gas. Iron oxide is removed as phyllite slag. Platinum's melting temperatures are significantly higher than other metals due to the presence of chromium, which makes them incompatible and requires special furnace design. The power capacity of platinum smelting furnaces reaches 19.5 megavolt amperes and 68 megavolt amperes. Energy consumption runs 800 to 850 kilowatt hours per ton of concentrate. Platinum's high melting point means impurities like iron burn off, and the result is a powdery sludge of platinum group metals: rhodium, iridium, ruthenium, and osmium, plus platinum itself. The converter's slag phase contains significant amounts of trapped platinum metals and gets recycled back to the smelting furnace to recover those captured metals. The converter mat gets cooled down, crushed, and processed at a base metals refinery. Here, hydrometallurgical processes dissolve the copper and nickel, leaving behind a residue rich in platinum group metals. This platinum metals residue heads to a precious metals refinery, where various solvent extraction and precipitation methods separate out the individual metals. Getting pure platinum requires further refining. Typically, this involves aqua regia, a mix of nitric and hydrochloric acids in a 1:3 ratio. Aqua regia is one of the few acids that can dissolve platinum. When the concentrate is treated with aqua regia, the acid produces chlorine, which bonds with the platinum, forming chloroplatinic acid. The final step uses ammonium chloride to convert the chloroplatinic acid into ammonium hexachloroplatinate, which can be calcined to yield pure metallic platinum. Platinum content in the residue after hydrometallurgical processing can reach 5,900 ounces per ton. That's an enrichment of nearly 500 times compared to the original flotation concentrate. Now, a bit of history. In 1735, Antonio de Ulloa and Jorge Juan y Santacilia witnessed indigenous Americans mining platinum while the Spanish traveled through Colombia and Peru for 8 years. Ulloa and Juan found mines with whitish metallic nuggets and brought them back home to Spain. Antonio de Ulloa returned to Spain and established the first mineralogical laboratory in Spain and was the first to systematically study platinum, which happened in 1748. In 1783, French chemist François Chaboneau was the first to obtain a pure sample of platinum metal. In 1801, English scientist William Wollaston invented a method for efficiently extracting the metal from ore. Growing demand for the metal led to the discovery of major deposits in the Ural Mountains in 1824 and in Canada in 1888. This ultimately led to geologist Hans Merensky's discovery of the largest platinum deposit on Earth in 1924. Platinum is primarily used in automotive catalytic converters. In 2014, out of 218 tons of platinum sold, 98 tons, 45%, went to vehicle emission control devices. 74.7 tons, 34%, to jewelry. 20 tons, 9.2%, to chemical production and petroleum refining. 5.85 tons, 2.7%, to electrical applications like hard disk drives. The remaining 28.9 tons went to various other minor applications, such as medicine and biomedicine, glassmaking equipment, investments, electrodes, anti-cancer drugs, oxygen sensors, spark plugs, and turbine engines. The most common use of platinum is as a catalyst in chemical reactions, often in the form of platinum black. It's been used as a catalyst since the early 19th century, when platinum powder was used to catalyze the ignition of hydrogen. In automotive catalytic converters, it completes the combustion of low concentrations of unburned hydrocarbons from exhaust gases into carbon dioxide and water vapor. Platinum is extremely rare on Earth, occurring at a concentration of just 0.05% in the Earth's crust. Platinum often occurs chemically unbonded as native platinum and primarily as an alloy with other platinum group metals. Most commonly, native platinum is found in secondary deposits among alluvial sediments. The alluvial deposits used by pre-Columbian peoples in the Chaco Department, Colombia, are still a source of platinum group metals today. Another major alluvial deposit is located in the Ural Mountains, Russia, and it's still being mined. When comparing the rarest precious metals by annual mine production, platinum is far rarer than gold. We're talking about more than 15 times rarer by annual output. In 2018, silver, gold, and platinum mine production totaled 860 million ounces, 108 million ounces, and 6 million ounces respectively. Producing a single ounce of platinum requires about 10 tons of ore. For comparison, gold needs around 2 to 3 tons of ore to produce 1 ounce, while silver takes 5 to 10 tons per ounce. Global demand for platinum in 2023 was estimated at 7.5 million ounces. The world's largest platinum producer, Anglo-American Platinum, produced 1.75 million ounces of platinum in 2023. Russian company Norilsk Nickel produced 593,000 ounces of platinum in 2022. Every year, an additional 2 million ounces, 60 tons of platinum, comes primarily from recycling auto catalyst and jewelry. What makes platinum stand out is just how difficult it is to extract. Platinum mining is extremely labor-intensive. The KEL process represents a potentially significant improvement in platinum concentrate processing technology from an economic standpoint through dramatically reduced energy costs. Compared to matte smelting, electricity consumption drops by 82%, and overall carbon dioxide emissions decrease by 70%. And so, having traveled from a thin reef deep underground in South Africa, through blasting, crushing, flotation with millions of bubbles, through smelting at 1500 degrees Celsius, through dissolution in aqua regia, through precipitation with ammonium chloride and calcination, platinum is born. A metal 15 times rarer on Earth than gold, requiring 10 tons of ore to be processed for a single ounce, whose entire annual supply, just 180 tons, would fit in a single room. A metal that catalyzes chemical reactions, cleans the exhaust of millions of cars, and adorns fingers with jewelry that never corrodes. Every hour, somewhere in the world, a metal component weighing over 50 tons is manufactured, and a single microscopic error in its machining can trigger a multi-million-dollar catastrophe. Picture a crankshaft as long as a bus that must survive 1 billion cycles of explosive force, or a cylinder block where a deviation the thickness of a human hair means scrapping a multi-ton giant entirely. But here's the mystery. How do engineers achieve micron-level precision when machining parts heavier than a tank? What happens in that secret quality control room, where a computer measures thousands of points and can shut down the entire process? And most importantly, stick around until the end, because I'm going to show you the final operation where one tiny slip turns months of work into scrap metal. This is manufacturing where every thousandth of an inch is a matter of engine life and death. Ready to look inside? The first thing that hits you at this facility? The sheer scale. Forget your average car engine. Take this cylinder block, for example. It can weigh dozens of tons. This isn't just a casting, it's a complex, multi-layered masterpiece of foundry art, requiring special grades of steel or cast iron that can withstand unbelievable loads, temperatures, and pressures. And here's the crankshaft. In big engines, this thing can be as long as a small bus and weigh just as much. This component is probably the most critical. It has to endure the explosive force of fuel combustion, converting it into rotational motion. The blanks often arrive as massive forgings where every pound of metal already has its own story. The process starts with incoming inspection. Specialists check the chemical composition, scan for internal defects using ultrasound and X-ray equipment. Because even the tiniest hidden flaw in a part this massive could lead to catastrophe during operation. It's like a health checkup for a steel giant. Only after a thorough inspection does the blank get clearance to enter the machine shop. Moving these blanks takes serious muscle. That's why the shop is equipped with powerful overhead cranes capable of lifting loads that outweigh most ordinary machine tools. Mounting the part onto the machining center is a precision operation requiring coordination and experience. This is the first step in turning metal into might. Now we move to the heart of the shop, the cylinder block machining zone. This is where multi-axis machining reigns supreme. Before you stands a gantry-type milling machining center. It looks more like a small house than a machine tool. Its spindles, fitted with ultra-hard cutting inserts, can remove up to several hundred pounds of metal per hour. The first operation is roughing. The goal, remove excess stock, eliminate surface casting defects, and give the part its basic geometry. The speed and sheer aggression of this cutting process? Absolutely mind-blowing. Those streams of hot chips tell you everything you need to know about the energy being dumped into this transformation. But the real magic happens later, during finishing operations. Remember when we talked about precision? For diesel engines, perfect cylinder geometry isn't just important, it's critical. That's where boring and honing come in. Boring creates the cylinder holes with micron-level accuracy. The slightest geometric error means uneven wear, compression loss, and ultimately engine failure. And honing, that's the final touch. A specialized tool with abrasive stones creates a micro-texture on the cylinder's inner surface, what we call crosshatch. This crosshatch is essential for holding oil and ensuring perfect lubrication of the piston rings. We're talking about polishing at nearly molecular level, guaranteeing engine life measured in decades. These machines operate under strict temperature control. Any temperature fluctuation can cause thermal deformation in a part weighing several tons, which means losing precision. That's why the shop floor maintains a constant microclimate, and the machining itself can run for days. Up next, meet our next hero, the crankshaft. This component works under the most demanding conditions. It needs not only colossal strength, but perfect balance. Manufacturing it, an engineering masterpiece. First up, preliminary journal machining. On specialized CNC turning milling machines, the connecting rod journals and main journals take shape. Given the weight and length of the shaft, unique support systems are used here to prevent sagging and vibration during machining. The critical stage, grinding. The shaft journals must have minimal surface roughness because that's exactly where friction with the bearings occurs. The smoother the surface, the less friction, and the longer the engine lasts. Special cylindrical grinding machines with highly sensitive sensors handle this job. Now, for the critical part, heat treatment and surface hardening. After grinding, the crankshaft journals undergo induction hardening or nitriding. What does this do? It creates a super hard, wear-resistant layer on the journal surface while maintaining the core's toughness and strength. This is essential so the shaft can withstand billions of load cycles. Think of it as armor for the engine's most vital component. Final stage, balancing. Given the massive weight, even a tiny imbalance can destroy the engine. That's why every crankshaft goes through dynamic balancing. If the machine detects a deviation, counterweights are added, or material is removed from the flywheel sections until the shaft achieves perfect balance. It's like tuning a violin, except instead of music, we get harmony of rotation and power. How do you achieve that kind of precision when working with such giants? The answer lies in the tooling and quality control. The tool itself is a high-tech product. Every cutter, every mill is equipped with carbide inserts or even synthetic diamonds. They have to withstand enormous temperatures and cutting pressures. Special coatings extend the life of these tools while keeping machining quality consistently high. In a dedicated tool room, there's constant monitoring of their condition, resharpening, and replacement. But the most important thing is quality control. After every key operation, the part undergoes rigorous measurement. Coordinate measuring machines help us with this. These machines, equipped with high-precision probes and laser scanners, can measure up to 1,000 points on a part's surface with accuracy down to a few micrometers. They create a three-dimensional map of the part and compare it to the perfect computer model. If the error exceeds the tolerance, the process stops, and the part gets sent back for rework or, worst case, scrapped. No part leaves the shop floor until the computer gives the green light on its perfect accuracy. And then, when all the components, the block, crankshaft, cylinder heads, connecting rods, have passed strict inspection and achieved perfect precision, they're ready for the final stage, assembly. This is a different shop, where sterile cleanliness reigns. Assembling an engine like this is no less precise a process than machining. All parts are thoroughly washed, removing even microscopic traces of metal chips and dirt. Specialists use torque wrenches to tighten thousands of bolts to a precisely defined spec. A mistake in torquing the cylinder head, for example, can lead to a blown gasket and engine failure. Every stage of assembly is tracked and controlled by electronic systems. Not a single bolt gets tightened without computer confirmation. After assembly, the engine heads to the test stand. Here it's fired up and gradually brought to operating conditions. Sensors measure temperature, oil pressure, vibration, power output. Any deviation from the norm, and the engine goes back for rework. Only after successfully passing all tests does the engine receive its quality certificate. These giants get installed on ocean vessels, locomotives, mining dump trucks, power plants. One of these engines can run for decades, churning out thousands of horsepower. And behind every hour of its flawless operation stand months of work by engineers, machine operators, quality inspectors. Manufacturing these engines is the pinnacle of mechanical engineering, where metallurgy, precision mechanics, and computer technology converge. And just like that, starting from a multi-ton forging, through rough and finish machining, through honing with precision down to microns, through heat treatment and balancing, through sterile assembly and rigorous testing, an engine is born, capable of running billions of cycles without a single failure. This is the story of how humanity learned to create steel hearts for the most powerful machines on the planet. Every crankshaft, every cylinder block, it's a symphony of engineering thought where an error of 1 micron means failure, and success means decades of flawless operation. When you see a massive ship crossing the ocean, or a locomotive pulling thousands of tons of cargo, remember, at its heart beats an engine, every part of which has passed through the hands of master craftsmen and the scrutiny of computers. This isn't just metal, it's the embodiment of humanity's drive for perfection, where precision is measured in microns and reliability in decades of impeccable service.
What if I told you the world's toughest roads and roofs aren't born on the construction site, but deep inside oil's blazing heart? A material that survives 360-degree heat and brutal cold. One mistake by the technologist, it turns to stone. But why did this black, sticky residue at the bottom of the oil column become the backbone of bridges, airfields, and massive warehouses? And what chemical secret lets it survive for decades without cracking under 40-ton trucks? Every year, the world produces hundreds of millions of tons of bitumen. It's extracted at temperatures between 930 and 1200 degrees Fahrenheit, squeezing literally the last drops from crude oil. Roofing felt? It passes through vats of molten bitumen at 570 degrees, where every inch of cardboard or fiberglass gets soaked in black gold. One wrong step in the process, and within a couple winters, that road's covered in ruts and potholes. Stick around till the end. You'll discover what even some manufacturers won't tell you.
Picture a massive oil refinery. Giant distillation towers, tall as a 20-story building. Crude oil flows in and gets heated to 650 to 750 degrees Fahrenheit. Fractional distillation begins. Light fractions, gasoline, kerosene, vaporize and rise upward. Middle fractions, diesel, fuel oil, remain in the center. And at the bottom of the tower, a heavy tail accumulates, thick, dark residue. This isn't bitumen yet, but it's already the base for it. This residue goes to a vacuum column. There, it's heated again, but under vacuum, at reduced pressure. This allows even more fractions to evaporate, which become lubricating oils and paraffins, without pushing the temperature high enough to break down the heavy molecules. What remains after this squeezing out of the heaviest parts, that's the foundation for bitumen and tars. But it's still a raw product. Next, chemistry kicks in. Into enormous reactors, they load this residue and add other components. For example, light oils, polymers, modifiers, sometimes sulfur.
At temperatures between 500 and 650 degrees, the mixture is held so large organic molecules partially cross-link, becoming more viscous and heat-resistant. Complex chemical reactions occur: oxidation, polymerization, condensation. Hydrocarbon molecules unite into even larger and heavier structures. The result is a thick, extremely sticky material that becomes solid or glass-like when cooled. It can be crushed into chunks, dissolved in organic solvents, or heated to a liquid state and applied as a waterproofing layer. Bitumen is a close cousin of tar, but with a clear focus on road construction and roofing. It's also derived from heavy petroleum residues after vacuum distillation. In large bitumen plants, it's less about pure chemistry and more about fine-tuning viscosity and temperature behavior. If the bitumen is too hard, it'll crack in winter. If it's too soft, it'll run in the heat at 200 degrees on the asphalt.
That's why the technology has a concept called penetration, how deep a needle enters a sample at a given temperature and load. Engineers tweak the ratio of light and heavy fractions, add polymer modifiers to get a material that won't flow in the heat and won't turn brittle in the cold. In massive mixers, bitumen is heated to temperatures from 450 to 650 degrees Fahrenheit, and under intense mixing, they add modifiers, mineral powder, sometimes acidic or alkaline additives to stabilize the structure. That's how polymer-modified bitumens are born, for high-performance roads, airfields, bridge expansion joints. When people say asphalt road, they actually mean a mix of mineral materials, crushed stone, sand, mineral powder, with bitumen as the binder. In huge asphalt mixers, the crushed stone is pre-dried and heated to temperatures close to 570 degrees Fahrenheit to ensure there's no moisture.
Then hot bitumen gets added and mixed until every single pebble is coated in a thin film of binder. The hot mix heads into dump trucks, then straight to the job site for paving. Get the bitumen wrong? A few seasons later, you're looking at ruts, cracks, and potholes. Nail the process? That pavement will handle years of trucks weighing dozens of tons. Roofing felt. It's the story of turning a simple roll of backing into a durable shield against rain, UV rays, and temperature swings. The base is cardboard, fiberglass cloth, or a polyester mesh in roll form, roughly 3 feet wide. Cardboard backing gets picked for budget materials and light-duty jobs, fiberglass when you need better heat resistance and less warping, and polyester for flexible roofs where stretch and tear resistance matter.
All these backings share one trait: they're porous, so without treatment they soak up water easily and fall apart fast.
To turn a bare base into waterproofing material, the roll gets run through a processing line with vats of hot bitumen or bitumen resin compounds. The liquid bitumen is heated to a range of 450 to 570 degrees Fahrenheit, sometimes higher, to lower viscosity and ensure quality penetration into the fibers. The roll is fed on rollers into the vat so that it's completely submerged in the melt and passes through at a controlled speed. During this time, bitumen fills the pores of the cardboard or fabric, displaces air and moisture, forming something like a skeleton flooded with waterproof mass. After exiting the vat, excess material is removed by calibrating rollers. This helps maintain the specified thickness and avoid drips. Next comes the stage of forming the coating layers. The saturated base passes under bitumen or resin applicators that apply the main layer on the bottom and top. For this, knife or roller coaters are used. A thin gap between the roller and support measures out the coating thickness.
The bottom layer handles adhesion to the roof deck or foundation, so it can contain more elastic plasticizers, polymers, oils, special additives that reduce the risk of cracking during bending and temperature swings. The top layer acts as armor against sun, rain, hail, and physical damage, so it's made harder and more heat resistant, sometimes modified with polymers for better UV resistance. While the top layer is still hot and sticky, it gets coated with mineral granules. A dispenser on the line drops a steady stream of mica, basalt granules, or slate onto the moving belt. The particles instantly press into the soft bitumen and lock in place as it cools. This coating isn't just for nice rough texture, it works as a shield against ultraviolet radiation. The sun heats the exposed bitumen surface less, the material ages slower and doesn't crack as fast. Plus, the granules boost abrasion resistance. After the granules are applied, the sheet moves through a cooling zone. This uses either air cooling or systems with water baths and chilled rollers that pull heat away from the hot bitumen. It's crucial that the temperature drops to a safe level before winding into rolls. If you roll up hot material, the layers stick together, the geometry gets thrown off, and the granules can lose adhesion. To monitor parameters on the line, they install temperature sensors and thickness gauges that ensure the coating layer doesn't come out too thin or too thick. A thin layer means future leaks. Too thick means wasted bitumen and problems during rolling and installation. The next stage is cutting and winding. The roofing felt sheet is cut lengthwise or crosswise into standard rolls, most often between 30 and 50 feet long. Each roll is tightly wound onto a core, so the edges don't shift and the upper layers don't slip. Sometimes one side is left with a strip without granules, covered with pure bitumen.
When laying, this strip gets overlapped by the adjacent sheet, forming a watertight seam that film or granules won't stop you from heating with a torch. Polyethylene or paper liners get added to the roll so the layers don't stick together during shipping and storage. The finished material gets labeled. The tag shows the type of base, the weight of bitumen per square yard, the type of surfacing, the flexibility temperature, and other specs that matter to designers and installers. The story doesn't end there though, because how roofing felt behaves on a roof depends heavily on what exactly got mixed into it back at the factory. If you take regular oxidized bitumen, the material will be cheap but sensitive to temperature swings. On a sunny roof, where the surface easily heats up to 360 degrees in summer, that layer gradually loses elasticity, becomes hard and brittle. To prevent that, polymers get added to the binder. Polymer modifiers make the material more flexible in cold weather and better at handling high heat.
Roll roofing can easily withstand both winter freezes and summer scorching without developing a spiderweb of cracks. It's polymer modifiers that gave Roofu Felt new life in the competition with membrane roofing systems. Picture a warehouse complex roof spanning several 100,000 square feet. The classic setup: leveled substrate, a layer of primer from bitumen emulsion, then several layers of roll material with a 4-inch overlap. The bottom layer is often torch applied. You flip it granule side up, heat it with a gas torch until the bitumen softens, and roll it onto the substrate. The top layer goes down the same way, forming a continuous blanket, where the seams are the most critical zones. The quality of that seam determines whether the roof leaks or not. And so, traveling from the bottom of an oil column, through vacuum distillation, through heating to 1200 degrees and oxidation, through vats of molten bitumen at 570 degrees, through coating with mineral granules and cooling, a material is born that protects millions of buildings from rain and snow, withstands 356 degrees of heat and minus 22 degrees of cold, serving for decades without a single crack.
What if a grass could be stronger than steel, yet softer than silk? How can a single plant be transformed into a floor that withstands a hammer blow and at the same time into a fabric that breathes better than cotton? Bamboo grows so fast it can shoot up by a meter in a single day, and a single plantation can